So I'm going to give a signal to the videographer, and we're going to get started, I think. Let me make sure this is on. On. Okay. So thumbs up here, thumbs up there. Everything is good. All right, folks. I'm excited to have you here with us. Just to make sure you're in the right room, right? We're going to talk about Scikit-learn and do an introduction to machine learning. I'm going to walk us through kind of a class overview, what you should expect, how this is going to roll out, and then we're going to dive right into it. First little bit, tell you a little bit about myself. We'll cover what we're going to do in the class, what you can expect, and more importantly, probably what not to expect. And then we'll look at how you can access the class materials, both here and after the class is over. My name is Chalmer. I always like to check the screen to make sure I'm the right guy. I like to stay busy. I work for a company called Booz Allen Hamilton. They're a technology and consulting firm, and our primary focus is to help people to change the world. And I feel like I'm successful some days at doing that, so that's a win for me. On the side, I founded a small programming school in Hawaii called the Dark Art of Coding. I teach people Python. I teach them data analysis and data science. With one of my colleagues in the back, Jeff, we founded Pi Hawaii. It is the largest and most active programming meetup in Hawaii. Here at PyCon, I help serve on the Python Education Summit Committee. So tomorrow there's going to be an education summit where educators can come together and talk about things. So I help with that. And for those in the audience who are interested in maybe contributing to an open source project, on Sunday night, I'll be with a number of my colleagues. We'll be running a Introduction to Sprinting tutorial. We'll walk you through how to use Git, GitHub, and how to contribute to an open source project. So come Monday, you can sit down with developers and you can help them to add features, fix bugs, and improve documentation on the projects you care about. This is my third PyCon tutorial. Prior to now, I've dove into Lion's Den on an introduction to bokeh, and I've done an introduction to statistics and probability. In really minor ways, emphasis on minor, I've contributed to bokeh, to pandas, to Jupyter, and a variety of other projects. This is how you can get a hold of me. All right. Today, we're going to move at a fairly rapid pace. I will take questions, but depending on the depth of the question, maybe the relevance of the question to what we're trying to accomplish, or whether I can even answer the question, I may defer your question to a parking lot. We might cover it at the end or after the tutorial's over. During certain parts of the tutorial, I might be able to support some kind of one-on-one conversations during exercises, etc., but that'll depend a little bit on our progress. There's an amazing amount of math under the hood when you do machine learning. There is almost no math in this tutorial. I think I've said math more now than we will in the rest of this tutorial. If you run into a significant snag that can't be rectified in a timely fashion, things just aren't working for you, something is not going right, do have 3 mentors who kind of walk around and will try and help. If for whatever reason we just can't get it fixed, your machine is not working, whatever, I'll invite folks, just take a deep breath, relax, enjoy the show, maybe lean over somebody's shoulder sitting next to you, and we'll see what we can do. I'll be happy to visit with people afterwards during PyCon or at the sprints to try and do a deep dive troubleshooting on your system to figure out what might go wrong. But my main ambition for today is to teach you to learn. Less so teach you facts, more teach you how to find facts on your own. So what I'm going to do is try and enable you to know where to look for more information, help you to explore some of the most commonly used grammar and vocabulary that is seen when you talk about machine learning. Nobody's walking out of here as a ninja, a guru, a rock star after only 3 hours. For you to get to that point where you feel really strongly confident in your machine learning abilities, that'll take time. It's going to take effort, practice, a lot of repetition, and plenty of extra study. But it's definitely possible. Each of our lessons is going to basically be a high-level overview of a concept. We're going to provide you some code examples. You'll be able to run those live in Jupyter Notebooks. After the code, I typically have some sections where we maybe have a deep dive and we describe a bit more detail about that topic. Or maybe I will outline some gotchas that I encountered in my learning journey as I was getting to this point. In order to kind of keep us on a schedule, each section is basically time boxed. After about X number of minutes, we're just going to stop on that lesson, and maybe I got partway through the deep dive, or maybe I got partway through the gotchas, and we're going to pause that lesson, and we'll move on to the next one. All that content in my talk track is all written in the Jupyter notebooks. So if we don't get to a particular thing, that's cool. You can always go back and reread my talk track and see the kinds of things that we want to talk about. At the bottom of every reference, at the bottom of every lesson, there's a set of references. There are links that will take you to other places where you can continue to learn things. In some of the sessions, there's going to be opportunities to do some hands-on exercises. When we get to an exercise, I'll give you a few minutes. You guys work on the exercise. A lot of them will be you researching topics very quickly and at a high level, but you researching. When you finish your exercise, put your green sticky up on the monitor. When I see a nice sea of green, I'll kind of know that everybody's done and we can move on. If you run into a snag, you put your red Post-it up on your monitor. One of my mentor folks will come and they'll try and help you out. Most of the lessons, most of the exercises and things in here will be fairly standalone. They shouldn't rely upon anything in a previous notebook, etc. So if a particular lesson doesn't work, something goes wrong, we move on to the next lesson. That should not impede your ability to execute any of the code in the next notebook. If you do run into a snag that we just can't resolve for you, I'd love for you to maybe make a note of that on one of your Post-its, because we'll collect the Post-its at the end of the day, and that way we can kind of go back and revisit the material and see what we can do to clean that up. We do have an opportunity for you to gain some experience points. This is your first exercise of the day. I'd like everybody to remind yourselves, I've got this. I'd like you to repeat that to yourself. And when you're done doing that, put your green Post-its on your monitors so I know you're done. All right. So there's a question in the front. Yes, sir. All right. Let's put an X on one of those for you, or put a big G. The one in your left hand needs a G on it. Excellent. If there's other colorblind folks in the room, I'll have somebody come and help you. That's totally cool. I do appreciate you asking. That was excellent. All right. There are three main ways folks can get to the class materials. We handed out the little slips of paper. For some folks, you might be accessing it via a Jupyter Hub that's fully interactive. Some of you might have done the local installs. That should also be fully interactive. And you can also get to the material via GitHub. And that material will be on GitHub even after you go home. I will be turning off my Jupyter Hub after the class is over. So don't save anything important on there, etc. But you should have access to everything via GitHub. All right. So that's pretty much the intro. I'm about to move into the next section. Before I do, are there any pressing questions that maybe I didn't quite answer or cover? Any thoughts? All right. For those who are not familiar with Jupyter Lab, on the far left side, you have a little folder icon. If you click on the folder, it will open up an Explorer-style window. We were in a folder called 0 Basics. I'm now going to move to a folder called 01 Intro. Okay? And in 01 Intro, I have a notebook called 01 Intro. All right. And this will be an intro to Scikit-learn. So we're probably going to spend about 20 minutes or so. All right, so my buddy Jeff mentioned that some folks were clicking on the student login and were running into some snags. Anybody tried to log in with that little student login slip and have a fail? Let me see a show of hands. I've got 1, 2, 3 folks. All right, for those folks, I'm going to highly recommend that you try and do a local install. I'm going to put a URL up here on the screen for you, and we'll see what happens. Okay. Instructions for folks to be able to do a local install are at machine install. All right. I'm going to leave that up there for a second. So those 4 or 5 folks who had some struggles, if you want to make a note of that URL, there's instructions on how you can install on your own local machines. All right. Cool. And if I move on and you haven't made a note of it yet, put your red sticky up and the mentors will come help you out. All right. There we go. All right. So let's talk a little bit about Scikit-learn and what Scikit-learn can do for you. In this section, we'll probably cover in about 20 minutes or so. We're going to explore some machine learning techniques, some tools, and some categories. We'll look at a high level of what supervised learning and unsupervised learning are, and we'll look at classification, regression, clustering, and we'll talk about dimensionality reduction. We will then talk a little bit about Scikit-learn, especially a thing that is referred to as the Application Programming Interface, the API. So machine learning is going to fall into 2 main categories, supervised learning and unsupervised. The process of unsupervised learning is associated with modeling a relationship between data and features of a data set and a series of targets or labels that you know about that data set, right? And when you have a model in hand that has a ability to identify a relationship between your data set and labels for your data set, you can then use that model to assign labels to new data that you've never seen before, or to calculate output values as you provide inputs. And what does that mean? There are 2 kinds of unsupervised learning we'll talk about here. First is classification, the second is regression. If I'm looking at a classification problem, for example, I might have some inputs, some texts, some emails, or comments. And my algorithm may be able to detect, is this spam or not spam? And so I can assign a label, spam or not spam, to an email or to a text or to a comment. If my inputs were data about flowers or insects or animals, say the length of some characteristic, the body length, the number of paws, whatever, I might be able to use that input data to assign a label to each animal. This is a dog, or it's a Labrador, or it's a poodle, or a husky, or whatever, right? So I might be able to classify things. If I am a store owner, online store owner potentially, or I'm a content delivery service, and I want to know details about my readers, my buyers, my viewers, based on some of the information I retrieve about them, I may be able to classify them in particular ways. This is a potential customer, this is a high-end, high-paying customer, this is a customer that is probably not likely to come back more than once, those kinds of things. And so with supervised learning, we have a set of data. We have labels for each of those things in the data. I can build a relationship, and now when I get new data that's not yet labeled, I can take that relationship and try and produce a label for something I've never seen before. With regression, the process is fairly similar. You have some inputs, and you can identify a relationship to outputs, but those outputs are what we call continuous quantities. They're typically some value. So say I have auto characteristics. I got a bunch of cars, and I know things about their color, their model, their age, etc. I might be able to identify a price on this kind of continuous spectrum. Say, this car with these characteristics should be priced at this value because it'll likely sell. If I am looking at my advertising dollars that I've spent, I should hopefully be able to predict what kind of sales revenue I have based on characteristics of where the dollars were spent, who they were spent on, etc. Next, if you have candidate characteristics, say you're doing interviews and you're looking at your candidates, maybe you can predict the salary you should offer them that they will likely to accept or receive. So that is supervised learning. We're going to go into that in a little more depth. We're going to see some hands-on examples of each of those. For unsupervised learning, this is a process of finding out a relationship amongst features in your data set in a way that classifies raw data without you ever having to tell it any input labels. There's a lot of algorithms that do this. A lot of these models try and replicate kind of how a human might think about things. If I looked at a scatter plot and I saw a bunch of things lumped together, I might presume that those things are related in some way. They're clustering together, they're probably similar. And so these algorithms tend to try and replicate what a human might do. We're going to talk about clustering in more detail. I'm just going to mention dimensionality reduction today. But with clustering and clustering analysis, you try to group a collection of objects so all the objects in one cluster are similar to each other, and they are more similar to each other than they are objects in a different cluster. Okay. So say I have a bunch of images. I might want to group those images together. Here's a dog, here's a muffin. Here's a human, here's a not human. Here's a celebrity, here's a not celebrity, those kind of things. If you have marketing data, you might want to identify traits about your customers. These are all customers that are similar to each other. These are customers that are different from each other. On social networks, you might want to do some analysis to try and identify communities of folks. These folks have similar interests. They have different interests. And though we won't get into dimensionality reduction in depth here, I'll mention it briefly. This is a process of taking lots of features, lots of variables that you might know about something, and reducing the number of random variables by trying to identify some principal characteristics. This dimensionality reduction can allow you to reduce the number of features that you have to do math on. It can help you to do feature selection or extraction. So I'll give you kind of an example. Let's just say I have a data set and it's got a bunch of different features related to coffee. Cup sizes, whether it's dark roast, not dark roast, whether there's flavoring added, nutmeg, vanilla, what country the beans came from, whether they were grown organically, not organically, whether they were sustainably harvested or not sustainably harvested. The preparation, it's latte, espresso. By the way, I don't drink coffee, so I don't know anything about what I'm speaking about right there. If I started to do some analysis, I might want to put all of these in here thinking, well, there's probably very complicated relationships amongst all of these things that might help me figure out what I should sell in my coffee shop. If you do some dimensionality reduction on this, you might identify some trends that might say, you know what, it's good that you collected all this data, but there's only maybe 4 things that really impact whether the coffee's going to sell, yes or no. And so maybe you might discover that cup size, the roast, the flavoring, the preparation are the things that actually drive sales. The other things are kind of maybe nice to haves, if you will. And so if you can do this reduction of dimensions, you can narrow down how much math you have to do and how much data you have to store and those kind of things. So that's the primary focus of dimensionality reduction. All right. When you do dimensionality reduction, you can save on computation time. You can save on storage space, both memory and or on disk. Sometimes if you have lots of dimensions, lots of variables, and you can shrink them down 2 or 3, you might be able to graph certain things in a 2-dimensional, 3-dimensional graph, and it might be easier to visualize. And sometimes it can help you interpret your outputs more easily. And one last thing, and there is a link to this, so if you're interested, you can go read it. There's a thing called the curse of dimensionality. A lot of people think, well, I should collect as much data as I can. The more data I have, the better, right? What we often find is that as you start to have more and more columns of data, it is often a little tricky to get all of the rows filled in a particular column. Maybe a customer didn't provide that data, or maybe that customer doesn't have that particular characteristic, or maybe this particular item doesn't have this nuance. And so you might end up with lots of columns, lots of rows, and lots of empty spaces in there because you couldn't quite collect it. And so your data ends up being sparse. And if it's too sparse, actually trending things can be a little tough. So dimensionality reduction allows you to kind of eliminate some of that sparsity of data that's characterized as the curse of dimensionality. All right, so that was a lot. Let's talk a little bit about Scikit-learn. We're going to see 3 of those different types of machine learning again. So Scikit-learn. Scikit-learn is a package, it's pretty well known, that allows you access to a lot of really common machine learning algorithms. And they provide you that access in a way that is tremendously consistent and well organized. It's their application programming interface. And what they provide to you is supported through very thorough and very comprehensive documentation. And you guys are going to have a lot of chances to dive into the documentation today. The API has very uniform syntax. It's very consistent in how it is designed. which is a benefit for you. As soon as you pick up your first model, you are well on your way to picking up your second and your third and your fourth and your fifth, right? Primary goal here for us today is for you to understand that API, for you to have an improved knowledge of the vocabulary of machine learning, and for you to figure out how to learn more, okay? So if we get past those goals and we succeed there, you're going to be very well poised to keep learning more as you go home and follow up. I have a link here to the API design paper. I've quoted a number of things here, so you don't have to go click on it unless you're really interested. But the API design is covered in what they call an API contract. And they focused on a number of things. I'm going to shrink this down in size a little bit. And 5 main things kind of stood out to me. They wanted it to be very consistent, right? So that when you need to put data into your model, you do it the same way every time. When you expect data out, you'll get essentially the similar types of data out. They provided a way for you to inspect your models. When you construct a new model, there is a way to figure out exactly what you added to the model. If a parameter value is generated by the model, there's a way for you to go find that parameter, like a coefficient for the slope of a line. You can go and get that back out. They have opted to avoid proliferation of classes. There are a number of tools out there in the world where they need to store data in some odd way, so they created a data type that is unique to their tool. They opted to avoid that. They said, you know what? Data sets represented by NumPy arrays or SciPy sparse matrices or maybe by data frames, that'll work for us. And so they've avoided creating random data types that are very specific to Scikit-learn. That allows you to take data directly from a model and feed it into some other component of your workflow. They have a focus on composition, and we'll see a really cool example of this where you can take the results of one model and feed them directly into another model using a thing like a pipeline. You can combine models together to do some very sophisticated analysis. And lastly, and this is probably the best part for me, if there is some operation you have to do and it requires you to decide and provide a parameter, they have provided a default value for you, and they've tried to make those as sane as possible. So basically, a number of the models, you can just provide data and run it, and it'll work well. You may want to tune it, and we'll talk a little bit about that. But by and large, the defaults are very sensible, and you don't need to really fuss with a number of those defaults for most things. All right. If you want to get some concrete details on how the API is put together, for folks who want to contribute to Scikit-learn, they have this Contributors API overview. But it was actually really good for folks even if you don't intend to contribute. It helps to highlight the pros and cons and the benefits and things that are going on under the hood. So that's good homework reading. When you go to use your Scikit-learn API, there's a number of steps. I have trademarked it. It's called the process. We're going to use the process repeatedly here today. The process in this case has got 6 steps. Prep the data, choose your model, choose appropriate parameters, fit the model, apply the model, and then examine your results. And by and large, most of the sessions will actually walk us through that. There'll be a heading that says, hey, now we're doing the data prep, now we're choosing our model, now we're going to use the appropriate hyperparameters, et cetera. But what does all that mean? In prepping the data, your data's got to be well prepared to be usable in the model. Preparation could include cleaning out corrupt data, things that aren't supposed to be there. It could be wrangling the data into a format that's more efficient or more effective. It could be normalizing your numbers to account for outliers, those kinds of things. And then your data is often going to need to be separated into what we're going to call a features matrix, and I'm going to talk about that more in a minute, and a target vector or a target array. And we're going to get into that. The whole next section talks about data handling, so we're going to talk about that in more detail. The next part, you're going to choose your model, and so you'll import a class from Scikit-learn. Say, hey, I want to do a linear regression, or I want to do a Gaussian naive Bayes. From there, we're going to select a set of hyperparameters. We'll put those into the model and get the model ready to run. We won't do a lot of that because, again, the defaults are already sane and they're already fine. Once we've chosen the parameters, we fit the model. We say, here's the data, run the model on the data, and start to build those relationships behind the scenes. Once the model's done running, we're going to apply the model to our new data. We put the new data in, we run it, and when we run it, if we're doing something supervised learning, we'll typically use a dot predict method. If we're doing unsupervised learning, we might end up calling a dot predict or dot transform method. And then as soon as that's over, we start to look at the results. And I'll show you ways to get the results out. I mentioned Scikit-learn is designed so you can do inspection. I'll show you how to inspect. But we'll also show you how to plot some of these things so you can see what they look like. All right. I'm going to do a quick demo here, but before we go any further, any questions, any thoughts? Okay. All right, so let's whet our appetite. Let's take a look at what we got coming down the hike. Again, I don't drink coffee, so I'm not sure why coffee plays such a prominent role in this particular thing, but I got online and I looked up all the local coffee shops on the north shore of Oahu, Hawaii. That's where I live. And I'm like, how much do people sell coffee for? And then I was horrified because like $4.50 for, all right. These are prices for different size cups, right? In terms of prepping the data, I needed to get those numbers into a format that Scikit-learn would use. I also wanted to be prepared so I could maybe plot a scatter plot or something. So I started off with a set of standard imports. That's generally where you start. I created 2 NumPy arrays. We'll talk more about the data handling part here, so I'm just going to hand wave some of this away. But I put in 6 numbers for the cup sizes and 6 prices for each of those cups. I put them in order so that there is a one-to-one relationship. 12-ounce coffee is $2.95. A 16-ounce coffee was $3.65. I called these X train and Y train. We'll talk a little bit more about that. But this is the data I'm going to use to train my model. I want to really quickly get a look at this, see what it looks like on a graph. So I'm going to dump this into a matplotlib scatter plot. I'll give you a few more details on that later, but let's cruise through this. Okay, let's start at the top. I'm going to execute the cells. Helps if you execute cells. For those who've not used Jupyter Lab before, or Jupyter Notebooks, I'm going to click in this cell, and I'm going to hit Shift-Enter, and it will run that cell. I'll know that it's finished running because there'll be a small number here to say, hey, I'm done. If it's still thinking, there'll be an asterisk. So I click in there, I hit Shift-Enter. I'm going to go down, I click in the next one, I'll hit Shift-Enter. And I go to the next one and click Shift-Enter, and we get a scatter plot. And so these are prices for 12 to 20-ounce cups of coffee on the North Shore of Oahu. All right, we've not done any machine learning yet. All we've done is graphed stuff. Okay. I mentioned that we need to get our data in a format that our machine learning library will use. When I made XTrain, it was a NumPy array. This is a technique you can use in NumPy to slice through all of the items in the array and create a new dimension. And we're going to talk about that in the data handling thing, so just bear with me. I've created an array that has a series of rows in it. Each of these things in the brackets is a separate row. All right. My Y training data can actually be an array. It does not have to be in a series of rows, so that part is fine. I have some friends, they're a little esoteric. They don't like standard size cups of coffee, or sometimes they do, but I have like 15-ounce cups and 17-ounce cups. And they're like, well, if I came to Hawaii, how much would I have to pay? All right. So I'm going to create a very small array that we're going to use for testing purposes, and I'm going to call this xtest. I'm going to convert that to a NumPy array with rows. A minute ago, I used np new axis. You could also use none. np new axis, for those who don't know, is just an alias for none. So now I've got a brand new array. All right. So what have we done so far? We've made a training set with cup sizes and prices, and we've made a test set with just cup sizes. We still haven't done any machine learning. Okay. Let's get started on the machine learning part. In Scikit-learn, they have a whole collection of modules that have classifiers in them. In the linear model module, they have a variety of regression types and linear types of classifiers. We're going to use the linear regression classifier. So Shift-Enter to execute that. I've now imported it. That's the choose the model part. We're going to assign the appropriate hyperparameters. We'll look at hyperparameters in a little more depth in a few minutes, but right now I'm just going to go with just the defaults. And I'm going to create an instance of this. When I ask Jupyter to evaluate this, it will spit out a copy of a string associated with it. And that string is going to tell me, here's all of the hyperparameters that got fed in. And each of these is one of those sane defaults. We're going to talk more about each of these in a bit, so bear with me. So we've done the choose the hyperparameters part. Now we're going to fit the model. When I fit, I provide it my training data, and it'll start to develop those relationships. So I'm going to give it my X training and my Y training. I'll do that. And it's done. Behind the scenes, it has calculated a relationship between the input coffee sizes and the input prices. That relationship in this case is a straight line. And for those who remember your math from high school, every straight line has a slope and has a place essentially where it intersects the y-axis unless it's vertical. So I can ask, what is the y-intercept for this line that got created, and what is the slope of the line? And it'll say, hey, I calculated that the slope of this line is 0.14, and this line should intersect the y-axis at 1.2. Okay, that's good. Now let's try and predict how much my friends would have to spend for their randomly sized cups of coffee. And there we go. Based on the fitting of the model and those two parameters, I was now able to calculate for 16 ounces, my friends should expect to pay about this much. For 15 ounces, they'll pay less. For 12, they'll pay significantly less. And for a 20 ounce, they'll pay the most. And that's it. You've machine learned. We can all go home. But let's take a look at the results. So I've got a couple scatter plots we're going to put up. The first scatter plot in this cell is going to show our X training data and our Y training data, and it's going to be in purple. I'm going to then do the X test data, my 5 friends' cup sizes, and the predicted prices. I'm going to do it in a slightly transparent color. That's what alpha means. Okay. And so there we go. Purple was the original prices that we knew. The pinkish color are prices that we are predicting. Somebody paying, getting a 15-ounce cup of coffee should expect to pay about this amount, right? So that's good. If you don't want to have a scatter plot of your results, instead of calling plot scatter, you can always call plot plot, and you can get lines instead for these. And it's the same data. Okay. All right. Sure.
Why did we convert data into arrays of arrays? Why did we add that second dimension?
Because Scikit-learn will crush your soul under its hobnailed boots if you don't. I'm going to talk more about this. We're going to get in the data handling part, and we'll talk a little bit about it. Yeah, Scikit-learn will crush your soul. I've got a couple more minutes for this little section, and then we're going to get to data handling, and we'll talk more about your thing. So I highly recommend that folks start to figure out what the API design documents and what the API documentation covers. And we're going to go through them in some depth as we go through. When I first started playing with Scikit-learn, probably my biggest struggle was, here is an example in a tutorial. It looks great. Let me do something very similar with my own data, and epic fails repeatedly. And it wasn't until I started to figure out, like, wait, it wants my data to be in a particular format did things start to run and work well. Up until that point, it was just horrible. All right. So I'm going to turn the time over to you folks for just a moment. There is a link here to the API reference. I'm going to ask you to open up the reference And you'll find a section on a model called Model Selection Train Test Split. Model Selection Train Test Split. Take a few minutes, about 2 minutes or so, high level, skim through it. If you see words that you don't know, make a note of those. Maybe we'll bring them up. Maybe we won't, right? But it'll be something for you to start to think about. And then there is a section in there that describes the type of data that the train test split function returns. What are you going to get back? So go do that. Give it about 2 minutes or so. When you feel like you have an answer for both of these questions, put your little green stickies up. I'm going to turn the mic off before Jeff says bad things about me.
Some of the folks that said they had issues was just the Jupyter Hub showing the regular notebook interface empty. But I mean, we can help them clone the repo there because I made one of the guys create a new notebook and do import Scikit-learn and it was working. So it's like,
We do not know what causes that.
okay,
It happened last Saturday to a couple of folks.
okay.
We thought it might be because they had already run the notebooks during my dry run, and we thought that there might be something cached in their browsers. But for someone who's new and was not in my workshop, for them to see the same problem,
It's a hazing bug.
yeah, it's totally freaky. I don't know what causes it.
So do you want us to tell them just install everything new or try using that one?
Why
Can
don't
we help them clone the things locally or?
So Git should be installed on each of those machines. Or Git should be installed on the Jupyter Hub because that's how I get my content down.
We can clone it there.
And we can also do a wget with a zip that
Yeah.
it's uploaded in master.
Yeah, if you want to work with them and see if you can get a copy of
Alright.
the material there, and just open it up.
I'm gonna pull my laptop and
Take a look at something real quick here. Let me show you guys a thing. They'll have their username, user student 100 or whatever, and it might say the word tree.
Yeah.
Just
Replace with lab.
replace it with lab.
the repository is under your GitHub profile.
Chalmer Lowe. Chalmer Lowe is all one word.
What's the name of the repo?
Machine learning. All right. If you're done with the exercise, post-it notes are up. See a lot of post-it notes. All right. Turn the thing back on. Any words pop up that you're like not familiar with? Shuffle split. Okay. Anything else?
Maybe matrix in this context.
Matrix. We'll talk more about matrices in a minute. So, all right. Anything else? It's good that you guys know all the things. Stratify. Interesting. Okay. All right. Some of these things we'll talk about. Some of these things I may not know all the details of. I'm not going to tell you which is which. All right. We'll leave that as a surprise. What type of data will train test split return? It'll return what? A list containing what? What type of data is going to be stored in the list? Whatever type of inputs you got? Okay. So let's pull this up. PI reference. TikTok. Control F. selection. All right. There we go. So as you start looking at these things, the API documentation is generally laid out in a fairly efficient way. It may tell you a few words about what the thing does. I will say that that tends to be a little sparse in the details. You might notice that they have a link to take you to the user guide. The user guide typically has a lot more detail about what does this thing do, how to use it, when would you use it, etc. They then give you a nice summary of all the parameters. And again, these parameters all have defaults, and the defaults are sane. And so it says, hey, when you feed data in, you're going to provide a series of arrays. Those could be lists. They could be some other things. Could be pandas data frames. They will give you some parameters on when you split your data into components, how should you do it. In the returns section, they will tell you what you get back from that thing, so you know what to expect. And it will tell you that it will be a list. It will be 2 times the length of the arrays, and it'll basically break out your content, right? And we're going to see an example of this. So, all right. We will use train test split multiple times today, so you'll see lots of examples of it. All right, there we go.
As I look at the examples, it actually looks like it returns more than just the returns multiple times.
Yeah, and we'll see that. We'll see that. Okay. All right. So now we're going to move to the next conversation. This will be section 02, data handling. Okay. All right. So in this conversation, we're going to explore the data types that Scikit-learn uses. We will explore several techniques to prep our data for use in Scikit-learn. We're going to see some techniques to manipulate the data or review the data. And we're going to look at a couple of techniques to view that data using Matplotlib. I will warn you right off the bat, this is not expected to be an exhaustive overview of data handling or visualization. I'm going to give you just enough so that all the other examples make sense. All right. By and large, Scikit-learn is going to use NumPy arrays, SciPy sparse arrays, and pandas data frames. To train a Scikit-learn classifier, you want to provide it a 2D array, a two-dimensional array. Often in literature, you'll see that referred to as a features matrix. Generally, to be labeled with an X, but maybe not. For the labels, you typically provide that as a single one-dimensional array. Often we'll call it a target array. It might be labeled with a Y. Okay. Your features are the things that you know. I know, for example, the cup size. If I was looking at insects, I might know the lengths of specific beetle body parts. The wings are this long, the legs are this long, the thorax is such and such a dimension. Right? And so, for example, with these two features, I have soda sizes here, and I have beetle dimensions there. This features matrix has only a single variable, just soda size. My second features matrix happens to have 3 separate variables, 3 separate features. There's the dimensions for the head of the beetle, the thorax of the beetle, and the abdomen of the beetle. In both cases, I have 4 samples or 4 rows. So features are the columns, samples are the rows. By the way, the beetle dimensions are completely fake. I'm also not a beetle person. So I don't do coffee, I don't do beetles. I don't know why this is in my presentation, but all right. Your targets, your Ys, are going to have a one-dimensional array, and those are going to be those labels or categories, right? Or maybe the prices that were spent on a particular thing. And so for my soda prices, it's just a straight-up one-dimensional target array. For my beetles, say I had 2 different types of beetles. I had checkered beetles and diving beetles. And say, if I looked at the dimensions of their abdomens and their thoraxes and their heads. If I noticed this beetle and this beetle are a little smaller than the other one, so this is probably one type of beetle and this is probably a different type of beetle. My target array may categorize those two beetles and say, all right, the first row was a checkered beetle, the third row was a checkered beetle. The second and fourth rows were diving beetles. Okay. The nuance here is, for every row in my features matrix, I should theoretically have a value in my target array. And that makes sense. If my features matrix for beetles has 4 rows, I need to have 4 classifications for each beetle to train my model properly. All right. Now, if we're doing something like clustering, you're not going to have targets. That doesn't make sense, but all right. So let's take a moment. We're going to look at how do we make these arrays. We'll talk about 4 or 5 ways you can make a 2-dimensional array and a couple of ways to make 1-dimensional arrays. Let's start off with NumPy. Again, we'll recreate the coffee cup stuff, make those. Notice I called this a lowercase x. When I change it into a features matrix, we're going to convert that to an uppercase x. You'll see that in a second. But let's quickly look at what this is. Okay, it's an array. Let's look at the shape of this array. This is a tuple. It has a 5, a comma, and there's nothing after the comma. This tells me that this is a 1-dimensional array, but it needs to be 2-dimensional since it's a feature matrix. And we'll show you how to change that. Y is a target array, and it can be 1-dimensional, that's fine. For those of you who are looking at this and going, why is there a comma? I do have some commentary there in writing. Tuples require a comma if you have a single value in them. All right. So how do I make that 1-dimensional array into a 2-dimensional array? Here's a technique you can use with NumPy. Basically says, take all the values in the array, does this slicing, take all the values from the beginning to the end, that's what the colon tells us, and then add a new dimension to it. And when I do that, notice I changed this to a capital X because we often use capital X's as our features matrix. And notice it went from being just a straight 1-dimensional object to being 2-dimensional. And if I check the shape, we'll see that it now has 2 dimensions. Still 5 rows, 1 column, if you will. All right. None is an alias, or sorry, np new axis is an alias for none. So that does the exact same thing. You can use either of these techniques. You see these a lot in tutorials as people are trying to shape their data for use. There's a third technique. You see this one, probably not as frequently, but it does show up. If your NumPy data is already 2-dimensional, here I've got an array with 1, 2, 3 rows. You don't have to do anything. You can leave it just as is. It's just that weird thing where your data starts out as being 1-dimensional that things get a little wonky. All right.
So there's essentially the data, it's essentially rows in your table.
Yep.
So if you have a 2-dimensional, you do need to basically transpose it so that each row has an individual unique value, or so like in your example with the beetles, we have 3 columns, right?
Yep.
But what if each row was all head values and the next row was all thorax values? Would you need to transpose it if you have a unique head, thorax, and abdomen value per row?
Yeah, because it's expecting every column to be a unique feature, a unique variable. This is my, like if I'm categorizing customers, this column is maybe how many children they have. This column is what their salaries are. This column is what kind of car do they drive, those kind of things. So every column is going to be a unique feature or a unique variable to assess. All right. We can do the exact same thing with pandas data frames. I'm going to make, or sorry, pandas series. I'm going to make 2 series. You might look at this and think, well, this is clearly 2-dimensional. It looks like a table. If you check the shape on this thing, you will find that a pandas series is actually 1-dimensional, which is part of what crushed my soul when I was first kind of playing with these things. I have this very clearly 2-dimensional looking thing, and I drop it into Scikit-learn, and all heck breaks loose, and nothing ever worked. So there was a lot of crying in my first few forays into Scikit-learn. To change a pandas series to a two-dimensional object, you can call the toFrame, and you can give it the name of what you want to call this series. There we go. And sure enough, it converts it from a series into an actual data frame. Data frames are always two-dimensional, and we check the shape, and sure enough, it went from being a one-dimensional series to a two-dimensional pandas data frame. If you have a data frame that has several columns in it, you may think, well, oh, I'm good. Clearly, a data frame column is obviously two-dimensional, but no. You have to convert the individual series into its own essential standalone data frame to make sure that you get 2 dimensions for the series. Okay. Another technique to do this, if you have a set of data and you want to convert it into a data frame, you can do this. There you go. I don't want to spend too much time on that. You can go back and look at this at your leisure. You'll see me use 1 or 2 of these commands in future lessons and be like, okay, now I know why he's doing this. He's making it into a 2-dimensional array. Okay.
Does that make Scikit see the row ID as the data?
I don't know that Scikit-learn cares about the row ID because when you use NumPy, NumPy doesn't have row IDs. It just, in its head, it needs it to be in a 2-dimensional format, and this is 2-dimensional from Pandas land. So, yeah, it's a thing. All right, so let's take a deep breath. How do we look at the data that we have or that we get back? So let's take a few moments to consider that. If I had a NumPy array and it's 100,000 items long, I can't look at all of it. So I often want to see just a snippet, right? Maybe the top couple rows. So you can use a slicing syntax to take a quick look at just a couple of the rows. Here I'm going to look at rows 0 up to 3. In Pandas, you can use the .head command to look at a certain number of rows. Here I'm choosing 3 again. In Pandas, you can also use this slicing syntax. So you'll see me call up data out of our machine learning outputs to take a look at these to see what we got back. All right, so we're going to step away from just Pandas and NumPy for a second. We're talking about naming conventions. I've kind of alluded to the fact that by and large, in a lot of tutorials or examples, you'll see things labeled as capital X to be your features, Y might be your targets. You're going to see that a lot. When you see capital X or you see your features matrix, generally this is the stuff that you already know. And it is potentially related to the target. I say potentially, we'll cover that in a sec. You will also see, though, that people will mention, hey, my features matrix is my independent variables, or they are my observed variables, or my explanatory variables, or my input variables. So you'll see all these verbs and words and nouns and stuff. I don't do grammar either. Coffee, Beatles, and grammar are not my thing. You'll see all these words. What independent means here is that these variables, these components, do not depend on something. When you say observed, it means you've observed this, either the sales of things or you've gathered data on your Beatles, whatever. Explanatory means it will explain the results that you get back later, or input should be self-explanatory. Some folks will label them as lowercase x. Some people will use capital X. It's going to vary. For those targets, those labels that you assign to things or that you get back, you'll see those referred to as dependent variables. They depend on something else. They depend on the inputs. You might see them referred to as unobserved variables or the explained variable, the outcome. You'll see Y's either lowercase or uppercase. Why do I go through all this? As you're going through tutorials, everybody's going to refer to them as something completely different. And so sometimes comparing one tutorial to another, and you're like, what is this person talking about? When actually they are talking about the same thing, they're just using different terms. When I mentioned that sometimes the features are potentially but not always related to the target, what does that mean? Well, when we do machine learning, we're trying to figure out, here's my features and here's my labels or my categorizations. Is there a relationship? And if there is one, can I predict something in the future? But sometimes you might have a column of data or a variable that is completely unrelated. It's completely non sequitur. And so sometimes your features may not actually provide any input into what labels applied to something. Right? All right. There's another word that you're going to hear a lot called training and testing. Some data is going to be referred to as training data. Some of it's going to be referred to as test data. By and large, throughout the rest of this session, I'm going to kind of settle on 2 or 3 different terms, and we're just going to stick with those. Just be totally aware, your mileage is going to vary because everybody's got their own naming convention for how they label stuff. All right. So let's take a quick look at that train test split function that we read a little bit about. When you do machine learning, it is crazy important that as you kind of finish your machine learning episode, that you take a moment and you test and see what you have accomplished, right? See whether things are working the way you expect them to, etc. And so Scikit-learn has got some components built in to allow you to do testing and training. And this is a very sophisticated process. There are a lot of different ways to do it. We're just going to touch on one of them. It is probably the simplest and easiest one to accomplish, but it may not provide you all the details that you need, and it may not provide you all of the fine granularity that you need to have. You will see references to maybe 3 different main types of data. You'll see the word training. You might see the word validation. You might see the word test. Sometimes people will use test and validation synonymously. Sometimes people will use them to mean 2 separate things. Often, if people are using these 3 things to mean different things, training would be, here, I'm going to teach my model about relationships. The validation might be, let me check to see if everything is working out the way we expect. And then once I've trained and validated my model and I feel confident that my model is doing what it's supposed to be doing, let me then test it with something where I know the actual results and make sure that it comes out the way it should. And you might say, well, isn't that what validation is doing? You would think yes, maybe a little no, maybe a little yes. I'm going to leave it up to you to kind of read that, but I want to put that thought in your head that training, validation, and test are important subjects, and you guys should start to consider those as you go down your machine learning journey. We're just going to focus on training and test. We're going to skip out validation. Okay. So how do you get training data and test data? Normally you break your data into 2 piles, and that's the idea behind train, test, split. I'm going to split my data into a training set and a test set. So I can import from Scikit-learn my model selection. From this module, I'll input train, test, split. So let's execute that. I have a data set related to coffee. Let's go take a look at it. I have a folder called Universal Datasets, and we have a couple of data sets that we're going to look at today. So you should get used to the idea of looking at your data, figuring out what's there. This case, I have 15 rows of data. These are prices for coffee of various sizes. Everything from about here down is completely fake. I actually pulled these off of menus on the North Shore, and the rest of them, I'm like, well, 12 ounces? That's about $2.90. What the heck? So yeah, fake data. It's all good. It's like fake news. Okay. So we will read this in as a data frame. Let's take a look at the data frame. Let's see. Let's say df. Sure enough, it read in successfully. I have 2 columns, one called size, one called price. I mentioned you could use something like data head to look at smaller snippets, so let's do that. There we go. But for my model, I just need the size column. So I'm going to convert that to a 2-dimensional array. I'm going to call it with a capital X. My prices, I'm going to use those as my target array. They don't have to be 2-dimensional. So there we go. Size is 2-dimensional, sure enough. Head is 1-dimensional series. Okay. So I've now taken my data, I've read it in, it is in a features matrix, and it's in an array. With train test split, I'll feed it my features matrix, I will feed it my target array, and I can tell it how to split it up. In this case, I'm going to say the size of my test data should be about 33% of the total data. So if I have 15 records, what's 33% of that? 5. I can assign a random state. So you'll see mentions of randomness a lot. Yeah, what's up?
Are there any canonical, like, thumbnail, ideas about how much you should reserve for tests?
Cool. There are. I'll show you one in a sec. Don't let me forget. So the random state, you'll see this a lot in Scikit-learn. A lot of the models have a mechanism for you allowed to put a random number in, and it's a seed. You say, well, what does that mean? If I want each of you to get the exact same results as I get, we can all provide the same seed number, and it will then do a pseudo-random algorithm to break things up in a particular way, and you'll all get the same random outputs that I get. Right? So that's what this seed is for, the random state seed. Let's run this real quick. When it breaks the x and y values out, it will break them each into 2 components. So I end up getting a total of 4 things out. I provided 2 and I get 4 back. And it's going to dump out a list. But a lot of people will take that list and they will do what's called list unpacking. And so even though I get back a single list, I'm going to unpack the first value out of list to this variable, the second value to that one, third and fourth. And so I end up getting all 4 variables out of my list unpacked, and now they have individual names, and I can refer to them one by one. And I can see that my new split off training data only has 10 rows, which is what we expect. My test data has 5 rows, which we expect. And my training categorizations have 10 items, and my test has 5. All right? We fed in a matrix, we got out a matrix. We fed in an array, we got out an array, and we had twice as many things out as we had in. All right, so Eric asked a question. He's like, hey, is there some canonical value about how you should split this up? Okay, let's take a look here. Let's start by looking at what is the default for a test size. And the default for a test size is 0.0 or 0.25. If you want to give it a float, you can say, give me some value for my testing cutoff as between 0 and 1, and it gives you a proportion. So I gave it 0.33. It held out 33% of my values. You can give it an integer instead of a float. And you can say, hey, I just want you to hold out 3 records out of the 15, and it'll do that as well. All right. You can also set the training size versus the testing size. There's a variety of things. So you could approach it from either saying, this is how much I want to hold off for the training size, this is how much I want to hold off for the test size. Either of those work. How did I pop that out? Good question. Okay, so here's a cool thing about Jupyter Lab. It is very much designed for interactive computing. So if I put my cursor in this cell and I click, for example, on any given function, and so train test split is a function, I click there. If I pressed shift and then press the tab key, it'll bring up the documentation for this particular thing. And you can scroll down in it. This is natural to me. I do it without thinking nowadays. So I just pop it up. I'm glad you asked. That was excellent. I use this feature in Jupyter Lab all the time. All right. Yeah. So up here in the Edit menu, if you want to clear all of the outputs, you can go to Edit, and you can go to Clear All Outputs, and they're all gone. If you want to clear the output for a single cell, whatever cell you're in, you hit Clear Outputs, and it'll clear the outputs for that one cell. Also good questions. All right. Did that help a little bit? Now, when you do validation, there are things called cross-validation. Let me see something here. So cross-validation, Scikit-learn. Do they have any pretty pictures? They have pictures. Am I going to say they're pretty? Maybe not. Okay. There are techniques that you can use for validating your models. One of them is k-fold cross-validation, where you might say, okay, I have this large data set. I'm going to break off a portion of it, and I'm going to use it for testing. I'm going to redo my model, though, a second time, and I'm going to grab a different portion of the data and use that one for testing now. I'm going to do it a third time and use a different portion of data. And so I end up running through my model 4 different times with 4 different sets of testing data out of there. And then I might take an average of these 4 results and say, you know what, now that I've done this 4 times, and I take an average, I know that it wasn't just a fluke that I got some result, because maybe these records were a little wonky. I can say I've looked at these and these and these and these, and with an average, I feel pretty confident that my model is classifying correctly. And you can get to the point where you can say 1 record at a time. You can say use 99 records for training and use 1 record for validation, and then check the next record and the 3rd record and 4th record. So as you start to figure out your training regimen and what you want to do, you'll start to research things like cross-validation and figure out, for this case, what's necessary. For this model, what's necessary or what's advised. But that gets crazy complicated, and you can see there's a lot of discussion here on this page about various techniques that you can go through. Cross-validation, evaluating the performance of your estimators. So in Scikit-learn, the classifiers or the models are often called estimators. Okay. All right. I think we've exceeded our recommended daily allotment of time for this. Let me make sure that there's nothing crazy here that we need to look at. Okay. I've got a couple of snippets of code in here I'm going to skip. I'll let you guys play with those on your own. Really quickly, I'm going to show you a couple examples of visualization things that we'll be using later. All right, so we're back in the data handling sheet, and we've scrolled down a bit. A lot of folks use matplotlib. You can use your own favorite graphing library, but this one is fast and easy. In this case, I have a set of data called linear reg train CSV. Let's take a look at it. This is completely random numbers. I pulled them out of thin air. I'll show you how I got them out of thin air later, but I pulled them out of thin air. I'm going to convert 1 column into a frame and 1 column into just a straight array. And with scatter plots, if you drop your x values in and your y values in, matplotlib will plot these things for you. And we're going to see lots of examples of us plotting things by putting x values and y values in. Yeah, okay. Mine does do it by default. That's an interesting question. And you used, was what, percent matplotlib what? Okay. Right. In some installs of Jupyter Lab, if you run this command, percent matplotlib inline, it will set up some feature in the background so that matplotlib will display properly in your Jupyter Lab, or your Jupyter notebooks. I do not know why this works in some cases but not others. It has been many moons since I've ever had to use that particular command to make it work. So I appreciate you bringing that up, because that's probably perplexed a few folks. I'll leave that in there for now. Okay. Let's see. But by and large, with scatter, you can put in some values, and it does it. It's pretty straightforward. A neat thing, though, is that you can provide additional details to your scatter plot that allow you to change colors based on the categorization of things. So I'm going to create a set of labels for my linear regression data set. My data set has about 25 pieces of data in it. I'm going to create a set of labels. And what this will do is if we were to look at all of the raw data and say maybe the raw data for this one and the raw data for that one and the raw data for that one, 25 rows of data, I might say that whatever's in row 1 is category 1, whatever's in row 2 is category 0, category 0, category 0, category 1. And so I might have categorized these things, and I can show those categorizations through color differences on the screen. Let's look at that, okay. How we do that is through the use of the color feature and the color map feature. I can provide the X and Y values, and then I provide the labels to this colors parameter, and for every 1 in my labels, that will be assigned a color. For every 0, it gets assigned a different color. The CMap is a way to provide a mapping to say, here's 2 colors to use red and blue in this case, and every time you have a 0, maybe apply a red, every time you have a 1, apply a blue, and it will map this out for you. And so now we get that same data, but everything here has been categorized in red, everything over there is categorized in blue. And so you're going to see examples of us using that categorization multiple times. Matplotlib has several defined color palettes. Red, blue is one of them. Another one is seismic. I'm going to use seismic pretty much the whole day. I would be interested in having a conversation afterwards with folks who might be colorblind, if there's anyone in the room with that categorization about these colors. All right. I'm going to cut you folks loose for a moment. I'm going to have you start to read ahead a little bit about the things we're going to cover next. All right, we're going to dive into a more in-depth discussion of linear models, in particular linear regression. So take 3-4 minutes and churn through this content. I've got 2 questions for you. I think this is also probably a good time if people need to take a quick break. We take a break about once an hour. So I'm going to turn the mic off, and you guys have about 3 or 4 minutes. Okay. Sure. So you can do shapes, but there's you have to figure out what the parameter is to make matplotlib do shapes. So bear with me for a second. Okay, choosing color maps. So matplotlib actually have an entire page devoted to strictly nothing but color maps. And so they have the Viridis or the magma color maps. They have grays, purples, blues. They got things that are kind of rainbow spectrum or things that are kind of all blue and green, whatever. They have things that are gray and various grayscale. They got a whole collection of them. And they have comparisons of a bunch of these, like, you know, if this was rendered in grayscale because you printed it on a black and white printer or whatever, how might this show up? Those kind of things. Uh-huh. this link actually takes us right to this section of the page. Awesome.
Very useful.
How very useful, yes. There is a tool apparently called VizCheck that can look for things. It says avoiding color maps with both red and green will avoid many problems in general. And I did read that. I'm like, oh, so both red and green are probably bad. I won't use both. I'll use red and something else. And yeah, apparently that's a fail. All right.
There's actually some color blindness simulators out there too, if you want to like test use Google forms, but they're kind of risky.
All right. By the way, when you finish these questions, make sure you put your little green stickies up. Now that we got past the data handling, the rest of this is basically machine learning. It'll be way more fun. So I did this for my local meetup. We had about 37 people come out. And we did this. We revised the entire thing after that. So you guys are getting the new and improved model. Hopefully it's reasonably improved. We'll see. All right. Quick answer.
So in JupyterLab, when you open a new tab, is there a new kernel or do they share variables?
Ah, awesome.
I'm not, I don't have much.
Click on the running man and see running. So open. Yep. Three different comic books. The console gets its own kernel as well.
So you can actually open up another tab and use the same kernel from another.
You can. You can use the same kernel in more than one tab. You can go into an individual cell and open up a console related to a notebook you already have running, so you have access to all of the.
When you're in a console, how do you exit the Jupyter notebook? Is there like a hotkey or is just the
Wait. Say that one more time.
When you're in a console or bad console and you open Jupyter notebook in a directory, how do you be in that aside from just closing the console?
You may see the shutdown looks nice. I'm going to give you, we'll give you this about the short amount of time to respond. Either yes or no. And if you don't respond fast enough, you go, oh, screw it. And then you just spin right back. So, at least that's what I'm doing now. All right, let's get rolling. I'm going to turn on the mic. So everything you say is being documented. And my esteemed colleague in the back over there is doing all the things with the videography. All right. So, answer to our questions. Who can identify a key benefit of the, and I cannot pronounce this probably, so we'll just call it Huber regressor model. What do you got?
Outlier detection, and that's can be a pretty big pain in the butt when you have to kind of go through and
Yep. when you do a regression, and we'll see a good example of this, right? When you do a regression, you're looking at all this data and you're trying to figure out what are the trends through the data. Well, sometimes your trends can be skewed if you have outliers. And so there's actually a model, actually many models, that will look at outliers and help to kind of suppress the influence of outliers on the model. That's cool. For the linear regression model, what are the ranges of scores possible? In particular, what did 1.0 mean? 1.0 means overtrained. Means perfect match, right? What are the range of scores? The highest is at 1.0, and it goes down to where? It can actually go into negative numbers, which means things are just gone completely off the rails. All right, cool. So I'm going to go into folder 3. We'll get into the linear regression conversation here. Tick-tock. All right. And I'm going to go ahead and shut down a bunch of my kernels because I don't think we need them anymore. There we go. All right, close these off. So this one we're actually going to spend most of our time looking at kind of the model itself. I'll give you a quick overview of what linear regression is. We will look at a quick code sample that walks us through the trademarked process. We will prep our data, choose our model, choose the hyperparameters. We're going to fit the model. We will apply the model, and then we'll examine our results. And depending on how things play out, we may do a deep dive into certain things. Might talk about some gotchas. We'll see what kind of time we have. All right. Linear regression models. These are really popular, partly because in many cases they're really fast. They generally come with very few tunable hyperparameters. We'll look at the hyperparameters for linear regression. I think there's only 4 if I remember right. Generally they're very easy to interpret. And often they will give you a really good baseline classification to start with before you even go down the road of, do I need some really sophisticated processing system or do I need to really dive into a very complicated model? This can often point you in the right direction before you go down that road. A couple cases where you might use something like a linear regression. Say you have ad dollars spent in various circumstances. You might want to be able to predict how many sales dollars will that earn. Again, if you have a car and it's a particular age, it's got particular characteristics, it runs, it doesn't run, etc. You might be able to help determine what your sale price will be. There's an interesting data set out here. It references latitude and skin cancer mortality, people who die from skin cancer. We'll look at that for just a second, and then we're going to breeze past it. Linear regression model that we're going to examine relies upon a thing called ordinary least squares, OLS, and is a way to figure out a linear function that fits your input data. I've got a quote from Wikipedia and a link to the Wikipedia article. What we do is we take the sum of squared distances between each data point and a corresponding line. And if we can reduce the sum of all those differences, we feel confident that our model better fits the data. So I would look here at this data point, and I'm saying that this blue line is probably a good fit. I would take this distance and square it, take this distance and square it, that one, and I take a sum. And I might look at other lines as well, and I might say, okay, well, what if my line was slanted a little bit differently in either direction? If I do that same math and square the distances between the dots and the lines, I will reach some nice kind of middle ground where that total sum is the smallest I can get. And if I can get to the smallest sum, I can feel confident that my line is kind of basically nicely in the center, if you will. And I use the word line. This is two-dimensional data, and so a line makes sense here. If I had dots, if you will, in a three-dimensional space, I might separate those out using some sort of a curve. Or if I have four-dimensional, I might have a hypercurve. So you'll see people refer to a curve or a surface. They basically mean the same thing. Long story short, you calculate all the distances to your surface, and you try and minimize those squared distances. All right. And what you end up getting is some sort of a line, or some sort of a surface. I have a very simple formula here. Some of you might remember back to your high school days and be looking at this in horror. All right. If I have a value for x, and I know the slope of my line, I know that angle the line is at, and if I have a place where that line intersects the y-axis, I can figure out what the y data point is. Right. So given some value of x with a slope and an intercept, we can calculate y. And that's as mathy as we've gotten. We're done. Okay, smiley face, no more math. I'm going to leave it up to you to dive into the math. There's a lot of linear models, and they sometimes use calculations besides OLS. Ridge is one of them. Lasso is one of them. We spoke about Huber for a minute ago. And there's many more. Everyone has a slightly different approach to trying to calculate that line or that surface that fits the data. Ridge tries to address some issues related to OLS by making sure that the coefficients are small in size. If you get a large coefficient for any value, say a large coefficient for the m, right? If you ended up getting a large coefficient, that can skew things in potentially undesirable ways. So Ridge tries to ensure that the coefficients are kept small, and it has techniques to do that we're not going to get into. Lasso tries to encourage very simple or sparse models, models with fewer variables. Huber, it tries to look for those outliers and account for them in particular ways. All right, so let's get into it. We'll start by prepping our data. Typically, I start with standard imports. I know that I'll probably want to plot something. I know that I may or may not be using NumPy pandas. I typically just dump those in right off the bat just in case. And of course, we import Scikit-learn. I have a note, and this is in pretty much every one of these. If you already know what model you're going to do, or you're going to use, you could potentially just import it right here with the rest of them. I have purposely broken that step out to a later component, but there's no reason you can't do it first if you wanted to. All right. So we've got this skin cancer text data. Let's go look at it real quick. It should be in my universal data set. Skin cancer. There we go. Okay. And theoretically, we have skin cancer data, latitudes, the number of people who passed away. That's the mortality column, the mort. I don't even know what ocean meant in that particular case. We have a longitude. Those are the latitude, longitude, the centers of each state. And we have all of the states. And so theoretically, you may be able to look at this in data and get some sense that maybe at higher or lower latitudes, maybe there's more of an influence on skin cancer that might potentially result in more deaths. There are a lot of, if you do any reading about this particular data set, there's a lot of questions about whether this even makes any sense at all, and are there other types of influences that might be impacting things in ways that maybe override the strength of latitude and longitude, maybe the availability of health care and those kind of things in various areas. So this is simply for demo purposes. I am not saying that we should draw any conclusions about latitude or longitude on mortality and skin cancer. All right. I'm going to read in the CSV. This CSV is a little wonky. It uses some different delimiters than normal CSVs. And I'm going to feed in names for each column manually. All right, and so there we go. I'm using head. Head shows 5 rows by default. So there's our data. So the data is all 50 states, and yet I get 49 rows and 5 columns. Yeah, Washington, D.C. is in there. Alaska's not. Hawaii's not. So this is continental U.S., including D.C. So again, when you get your data, it really helps take a look at it, figure out what's going on in there, right? Is this what you expected? Yay, nay? I'm going to change the latitude into a features matrix, change y into or I'll use y as an array. Look at each of those. So there's latitudes, there's longitudes, latitudes and mortality. Okay. I'm going to split this data up. I've got 49 records. Let's kind of break it up into parts so we can do a little training and testing. I'm using a random seed of 42, and I'm using a .33 for my split. And there we go. All right, and we'll do a quick scatter plot. This scatter plot shows just my training data. So it should be about 32, 33 records, I think. I chose to put a label for X's and Y's to show latitudes, number of deaths, that kind of stuff. All right. And, you know, there's maybe a trend here. Get to different latitudes, fewer number of deaths. Go to lower latitudes, you get more deaths. So maybe we can get a cool line out of this. Next step, we choose our model. Again, we could have done this right at the beginning when we did imports, but I wanted to put it here because this is the step of the process, right? We're going to import the linear regression. We do this guy. Okay. All right. I mentioned that with linear regression, it's generally pretty straightforward. You don't have to fuss too much with the hyperparameters. There are 4 of them. If I wanted to know more about some of these hyperparameters, you know, I can do Shift-Tab on this, and it'll bring them up, and I can scroll down to start to look at some of them. So if I wanted to read a little bit more about them, I can maybe try and dive into what does fit-intercept mean, what should happen if it's set to false, if it's set to true. I can learn more about what does it mean to normalize this data, what happens behind the scenes when I do a copy X, what happens when I change number of jobs. You know, say I want to do this on a distributed network or something and have this computed in various places. So, all right. But even reading, quote unquote, the manual, right? Hyperparameters can still be really tricky to understand. I like to start at the documentation to see what they say. Good places also, people will ask this question or similar questions on Stack Overflow. And so, I had a question about how the fit-intercept parameter impacts linear regression. Someone else out there had the exact same question. And so we asked this thing, blah, 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 right? And there were 2 answers here that were fairly robust and walked through and provided some examples of what would happen and if I used fit-intercept equals true or false, and provided both code to demo it and the results that came out of it. Had notes here about, notice these 2 concepts that are going on, etc. It's got a little summation, right? So as you run into questions that the documentation doesn't answer for you, feel free to check your friend Google. Your friend Google will often be able to point you to people just like you who are asking the same kinds of questions. I will say, when I started going down the journey of getting into machine learning, in many cases it took several readings of things. I would read some piece of documentation and I'm like, yeah, no, I don't understand that. And I might read multiple sources, and I go, oh, wow, this one says this, and this one says this, and this one says this, and I still don't understand. Might take some tests, run the code in various ways, not get it to work, struggle for a lot, cry a little, and then eventually it works. Take people's examples and tests and run those myself. And that can be a really long and frustrating, annoying process before you start to wrap your head around your expected outcomes. And that's totally okay, because if that happens to you, you're just like the rest of us. Right? I feel like this most days. All right. So, we've broken our data up into parts. We've got it segregated into training and testing. Let's fit the model. Let's put the training data in and see what we get. And if I want to open up a new cell in Jupyter so that I can maybe play with this a little bit, I can put a cursor in a cell and hit escape and then press the B key. So cursor's in the cell, I press escape, and then I press the B key, and it opens up a new cell below the one I'm in. If I pressed A, it would open a cell above the one I'm in. So I've got model, dot, and hit tab. Whenever you have a object in Jupyter, and it has attributes or behaviors or functions associated with it, you can type the name of the object, you hit the dot, and if you press the tab key, it'll open up a list of these options that you have available to you. And so with this model, I have a coefficient available, I have an intercept, I have some functions like fit or predict. I'm going to go look at the coefficient. Whoops. And so this thing has a slope of -6. And if we go back, so sure enough, it has a negative slope. Okay, so that sounds cool. We had an intercept as well. Intercept. And it intercepts somewhere around 388. So if this thing were to continue to go over to 0, and I was to look on the y-axis, it would probably intersect somewhere around 388. So that's good. Okay. All right. So this thing can produce a line. If I provide it with new data points, it should be able to predict where on the line those fit. And it should produce 17 of them, which is about 33% of 49. And so these are all the expected number of folks who may die from skin cancer at various latitudes. All right. So let's graph these. All the purple were the original training data. All of the pink ones are our predicted outcomes. If you don't like the dots, we can use plot, and we can make a nice red line. All right, and you can always pull up your coefficients and your intercepts. All right. So let's talk about gotchas. I kept messing up the formats of my data. I kept trying to feed it the 1D arrays instead of the 2D feature matrices. I'd pull up some tutorial online and I'd try and follow it, and it was a fail, right? So just keep in your heads that when you're doing this and you're testing your own models, make sure that you're feeding it the right types of data. A couple of thoughts to help you as you go down the road of learning stuff, some tips and hints. Read the outputs. When Jupyter provides you with some form of output, say, for example, right here, when I do a fit, Jupyter spits out this text string. Take a deep breath, check it out. Some of the things you'll recognize, like you might see fit intercept in multiple models. You might see end jobs in multiple places. The things that you don't yet recognize, be a little curious about those. Maybe go look some of those up. And using a thing like, Shift Tab to bring up the help documentation can allow you to start to scroll through these. I will say that in many cases, when I scroll through these and I come across a term or a phrase, I often don't know what it means right off the bat. And sometimes the documentation is sparse enough that I still don't know what it means even after I've read the documentation. But that's cool because your vocabulary will start to increase. And the next time, the third time, the eighth time you see that word, it will click and things will start to gel. You'll see that word used with other words, and now concepts will kind of come together. So read what it spits out for you. I work with students all the time, and Python and Jupyter spit stuff out on the screen, and they don't read it. They don't read it at all, and it blows my mind. Take a deep breath. Even if you don't understand it, just take a deep breath, read it. All right. It's that regular exposure to arguments that you might end up using in one model or another, regular exposure to terms, the vocabulary that will help to build an understanding of the inner workings. Totally recommend that you do outside research. When you find a new word that you don't know, go hunt that word down. Wikipedia, other places. The statistics descriptions in Wikipedia are very robust, probably too robust. But again, you're going to start to learn new vocabulary, and that's a good way to do it. Case in point, the word regression has been a thorn in my side since the very first time I saw it. I have not quite grokked what the word regression meant. I'm like, what is a regression? In my head, I kept thinking, like, if something regresses, it goes backwards, or it decreases or something, right? And I was trying to figure out why is a line drawn through a bunch of points called a regression? And this really, really, really stressed me out. And I kept looking, and eventually I came across an article that describes the term regression was actually coined by a guy named Francis Galton in the 19th century, and it described a biological phenomenon. He looked at the descendants of ancestors who were tall, and he saw that they tended to regress and get shorter. So if you're a tall person and you have kids, eventually your kids basically come back to normal. And this word has now entered the lexicon to describe changes in data points over time, even though it doesn't really mean changes in data points over time, if you will. So there you go. All right. Before we get into the exercises, we've covered a lot of stuff about linear regression. What questions do you guys have? What you got?
Is there a way to view the error? Like on the last example, our predictions were pretty wrong. I was wondering if Scikit has like a quick error, RMS or something like that.
Is there a way to look at errors? I'm not 100% sure I'm tracking the question.
Like the goodness of the fit.
Oh, okay. So Scikit-learn has a wide variety of techniques to allow you to kind of evaluate what we'll call scores or metrics for your models. And API reference, so score. So look up score. So you can quantify the quality of your predictions. They have an article here that they discuss that. You can look at things like your accuracy score. They have particular types of scoring mechanisms for many of the models. If we were to look at, okay, if we were to look at our model, most models will come with some sort of a scoring method, and the scoring method will give you some sort of a coefficient related to your prediction. And in this case, it looks at, I think, OLS, and tries to define how big of a deviation do we have, gives you some ranges for what the best possible score is going to look like, talks those things through, right? And various models use different types of scoring. Some of the techniques to get the scoring to work right may vary between models. We are not going to dive into looking at scoring in this particular conversation. We're not going to have enough time by the end of the day, but it's there. And it's there for every model. Any other questions? What you got?
How would you express the intuition behind the method name fit? What is fitting?
Fit the data. So you're applying a model, right? I mean, I don't know that I've ever had a whole lot of concern about the word fit, right? You have data. You fit this algorithm or this model to the data, and now it matches that data. We will look at underfitting and overfitting in a few minutes, and we'll see what happens when the fit is not right. But fit has always kind of made sense to me, I guess. So, all right, what you got?
My question is, we get the example of the latitude and the test, and at the end of the day, you get a bunch of numbers, but when do you know that you could actually use that, right? Like, can we take that prediction or that model and use it on other predictions of latitudes across the world, or like when do you know you're done?
When do you know you're done? All right. So part of that is going to be understanding the validity of the data that you're getting out of it and using scores. So here is my input data. Here's my predictions. For my test data, I know what the prediction should have said, and I know what it does say. And so you can score that and see how far off your model is. If your model is really, really good, you'll get maybe a high score, 0.9, something like that. Don't quote me on that number, dear Lord. High score means different things in different scenarios, or you might get a really bad score. There are what they call learning validation curves and learning curves for models, and depending on how you tune those hyperparameters, you can get your model to be more and more accurate. It'll almost never be 100% accurate. But there's an entire, we probably talked 4 or 5 hours on just that topic alone of how do you score your model, and how do you confirm to your liking that the model is accurate enough to use? So there's no good, easy answer, but it is a process, and there's a lot of documentation in the API references and the user guide about how to do that and what to look for. And there's a lot of tutorials that cover things like that as well. I don't know if that answered the question, but
So like, short answer, you wouldn't take the one we just did and revisit it?
I wouldn't use that because I don't know what the data is. I don't know where the data came from. And I think there's a lot of really weird things behind the scenes that might influence skin mortality. So, but anyway. But yeah, it really is diving into the scoring and diving into how well does your predictions track your known good data. But when you get into clustering, there is no known good data, so that opens a whole nother can of worms. And we'll look at clustering in a little bit. So it's not easy. All right. 307. Okay. Let's see here. Gotchas. We did that. Outside research. Good to go. All right. I'm going to turn the time over to you to do a little research here. Next model we're going to look at is a model called naive Bayes. In particular, we're going to look at Gaussian naive Bayes. There is a link here to take you to that. I'd like you to answer a couple questions. There is a method in naive Bayes that you can call that allows you to update your models over time. What is that method called? And then there is a link to the user guide in there. Find that link and then skim the overview. They mention two very specific places where naive Bayes classifiers have worked really well in real-world situations. What are those two cases? And we'll come back in about 3 minutes. so I'm about ready to roll. So we had a couple questions. What method in the Gaussian naive Bayes classifier can you use if you have a data set that's too big to fit into memory all at once, or you have a data set that you get new data periodically? Partial fit. So we've seen fit, they have partial fit. You get new data, you can essentially layer that in to your naive Bayes classifier. And a number of the models have partial fit capabilities. Not all of them do. All right. There was a link to the user guide. There were two very specific cases that they called out as naive Bayes worked really well in real-world situations. What were those two cases? Say it again. Document classification and spam filtering. All right, cool. So let's go look at naive Bayes. So naive Bayes classifiers, they're also very popular. They're crazy fast. They're generally simple. They have very few tunable hyperparameters. If you have data sets that have lots of columns, lots of variables, they're suitable for those types of data sets with high dimensions. And again, they can make a really nice baseline to help you kind of get a sense of where's your data going before you spend the time, energy, and money of coming up with some really sophisticated models. As I was putting this together, like the day after I started writing some of this stuff, this tweet showed up in my feed, and Sarada mentions that she made a bet at work. Her company does neural nets, and she bet somebody, I guess, that hey, they could do humor recognition, document recognition, if you will, just as well as this very complicated neural net, and she won. So a lot of times, the solutions we're trying to engineer do not require incredible amount of sophistication. You often want to start simple, see if that is good enough. We talked about a question like, how do I score things and determine is my model good enough? Well, if you do something that's fast and dirty and it's good enough, you can stop there. And you can spend your valuable time and effort on something more important. All right. So naive Bayes classifiers, they rely upon a thing called the Bayes theorem. And what Bayes theorem allows you to do is predict the probability that a label will apply to something if you're given a set of features. So the probability of a label given some features. And that's where we're going to stop with the math. If you want to dive into the math, I do have a link to my tutorial on statistics and probability. It was in PyCon last year. We talk about a wide variety of things related to just statistics and probability, but we do mention naive Bayes, and we go through an example of how you can use naive Bayes. All right. Okay. There are about 4 different naive Bayes classifiers in Scikit-learn. They use the word naive because they make certain assumptions about the data. If your data doesn't fit within the confines of those assumptions, you're not going to get good results. If they do fit nicely in the confines of those assumptions, then everything's going to work out fine. Each of these different classifiers has different assumptions. We'll look at Gaussian. It's going to presume that the likelihood of any given feature follows a Gaussian curve. And for those who are not into statistics, you may go, what the heck is a Gaussian curve? You might have heard a bell curve. Your grades fit on a nice bell curve in school. A Gaussian curve is essentially a bell curve. Most frequent things will fall right in the middle. Less frequent things will fall out on the outskirts of the curve. And so if your data fits that kind of a profile, like I might have lots of things that fit in the middle, but certain characteristics of my data will be fairly rare. If you have that parameters for your data, Gaussian may be a good fit for you. All right, so let's go through the process. All right, so we import the stuff. I'm going to read in this bananas data set. We'll look at the first couple of rows. We see that the rows are provided with lengths, widths, and a category. We're looking at 2 types of bananas. There is the Cavendish banana and the apple banana. Apple bananas are very common and popular in Hawaii. The Cavendish is the one you folks buy. Average length for Cavendish is going to be in some range. Apple bananas will be in a different range. I think the 190s is probably the apple bananas, and the Cavendishes are around the 200 somethings. By the way, this is all fake data too. I used a random algorithm to generate this data. It's close. I looked up how long an average apple banana is, and I looked up how long an average Cavendish banana is. But banana science is an amazing thing. Absolutely amazing thing. There's actually I think a Freakonomics podcast all about bananas, and the Cavendish banana in particular. So if fruits are your jam, you should go after that. It's good. All right. So I'm going to make my features matrix, and I'm going to grab 2 columns out of the data frame because I want to consider both the length of the banana and the diameter of the banana, or the width of the banana. And so this is going to be a 2-dimensional matrix. The categories for the bananas, whether they are apple or Cavendish, that is just an array. Oh, that worked out good. Let's look at our data real quick. Tick, tock. Okay. So I've pulled out these guys, and I've pulled out the categories, zeros and ones. We're going to do the train test split, test size. I'm using the same numbers I always use. We do have a place where you guys will do some modifications to the code later, and you'll see what some of the changes might yield in a couple of instances. Let's see what we got there. So a couple thoughts here. I'm actually going to cycle through each of these outputs, xtrain, xtest, ytrain, and ytest. And I'm going to look at just the first 2 rows of my training data, my test data. We're going to look at the size of that matrix. So there were 67 records out of 100 related to my training. There's 33 records out of 100 related to testing. Okay. All right. And let's map these on a scatter plot. All right. Everything in the upper left column part here is all blue, and that'll be one type of banana. Everything down here at the bottom, that's going to be all red. It's a different kind of banana. So Cavendish, I believe, is category 1, and it's red because it's a really long banana. Apple bananas are short and kind of fat. All right. They do taste a little like apples. It's creepy. Okay. All right. In the next plot, I'm going to plot just the test points, and we're going to make them a little faded in color using alpha. So these are all bananas. I don't yet know what they are. I'm not sure if they are Cavendish or apple. That's why we're doing this, right? So I want to try and figure this out. We're importing Gaussian naive Bayes, and we're going to choose the appropriate hyperparameters. You'll see that it only has 2. It has priors, and it has variance smoothing, and it's set to this ridiculously, I can never do scientific notation, ridiculously small number. Right? So if you want to know more about that, you can read about that. Okay. But again, easy to apply, almost no hyperparameters, fast and dirty. I've now fit my model, and I'm going to now use my prediction capabilities to say, here's those values that I don't yet have a category for. Let's figure out what the categories are. I had 33 that didn't have categories, so we should get 33 out, which we did. Here's the first few. And so it shows a bunch of zeros and ones. It's all good. And let's go see what we get. I'm going to plot the training data that we fed into the model. I'm going to plot the test data and the predictions that we got out of the model on the same graph. And there you go. And so everything that's pretty pale, we see it also showed up as blue, and everything that's pretty pale also showed up as red. So this naive Bayes classifier was successfully able to identify all of these things should be in this category versus that category. There you go. Nice. All right. So let me tell you about some of the gotchas that I had when I was going down this road. I remember this distinctly. There was a lot of crying around this as well. Naming conventions. I got into a lot of trouble with my naming conventions. I spent a great deal of time earlier, I think probably when we were in the one of the earlier conversations where I talked about some people will call this Y, some people call it X, some people call it capital X, capital Y, some people call it, independent variables, etc. In my head, when I was looking at this, I was thinking, hey, these are all X values, these are all Y values, because that's how you plot stuff when you're in high school. You have an XY coordinate system and you plot X's and Y's. And so I'm picturing in Chalmers' head XY coordinates. But the X values are the feature matrix, and the X values actually were the length of the banana and the width of the banana. That X features matrix actually had, quote unquote, the X and Y coordinates in it. And so everything deteriorated from there. And so I'm trying to figure out how I get my X and Y coordinates into here and here when really my XY coordinates were this thing and my Y inputs were actual labels. They were categories. This is banana A, banana B. And so that really messed things up for me a lot. If instead I had approached this with, well, here's a latitude and a longitude, a price and quantity sold, or passing yards and the number of wins for a sports team, I could picture those as being graphed on the graph. And I would not have confused either of these with X's or Y's the way statisticians or mathematicians use. So sometimes as you go down this road, you might end up kind of messing yourself up because your algebra teacher or whatever got certain things stuck in your head. So don't let that scare you. It happens to most of us. All right. We keep drawing a bunch of graphs and we do a lot of data handling and stuff. And I don't want that to distract you from the machine learning. We have the data viz steps to help us kind of confirm that the machine learning is working or to see what the data looks like before it's going in. And we, by default, have to interweave that with our process and our scripts. But quite literally, these 4 lines are the machine learning. All that other junk on either end is just getting the data ready to go in or looking at the data that came out. Those 4 lines are your machine learning and you're done. We can all go home, right? So don't let the fact that there's 28 lines of code here distract you from this part is the machine learning. And as you are doing your machine learning studies, this is what you need to focus on. Now, when you're doing your data viz studies, there's a different part of our code that you look at. When you're doing your data prep or your data engineering, there's a different part of the code to look at. But that part, those 4 lines are the machine learning. All right. Another thing, another kind of gotcha, sometimes starting too big is too confusing. In some of my early forays into this, I'm like, I have this really great 12 gig data file that I downloaded off the internets. And I'm going to solve all the machine learnings. Yeah, you have no idea what that data contains, and you have no idea what the relationships might be, and you've got 89 different variables, and some of them are important, some of them are not, and you don't even know where that. Start small. For example, if I go back and look at my bananas, and I look at row 83, I would see that the length of that banana is 187, and the width of that banana is 36, and that banana happened to be category 0, which is an apple banana. You can actually predict a single value at a time. And so if I took something real close to 187 and real close to 36, let's go see. If I took something close to 187 and close to 36, that should fit nicely in this blue zone, and I should get a blue categorization out of that. So let's go try it. Let's put one single prediction in here, 187 to 36, and see if we get back a category of 0. And sure enough, we do. Okay, let's up the ante a bit. Let's put 2 items in to predict. This one is clearly in the long, skinny banana range, which is down there, the Cavendishes. This one is pretty close to the fat apple banana categories. I pulled those 2 rough estimates out of my data. This is row 28, row 93. You notice I kind of rounded them a little bit. And sure enough, I should get back a 1 and a 0, and I do. So feel free to kind of predict a thing or two at a time to help yourself wrap your head around what's going on behind the scenes. What is this really doing? Check your data, do a sanity check. If this had come up with a 0 and a 1, or it'd come up with something like a 5 and a 6, then you know something's gone crazy wrong, and you want to figure out what's going on. So sanity checks, pretty good. All right. So how do we learn more? You saw me kind of poke and play just a little bit with the prediction process. That quite literally is how you learn any programming concept. You change stuff and you see what happens. Notice this is in the essential O'Reilly series. This is essential for your learning process. Change stuff and see what happens. Okay. Even though I just mentioned, hey, those 4 lines are the machine learning, all that other stuff is the data handling or the data viz, get crazy familiar with your favorite graphing library. You being able to visualize your results is going to help you understand if your model is doing what you want it to do. So I hate to tell you, hey, you can learn machine learning, etc., but you really need to learn graphing too, right? Now it's 2 things you got to go home and study. But quite literally, you being able to see results in some sort of visualization is going to help, and is going to help you better succeed at the goal of data science. The goal of data science is meant to inform and thus enable action. And most people are not going to understand the math and all the craziness that you spew out at them. They're going to want a pretty picture or a brief description. And so if you have a good handle on your graphing library, you can provide them with a well-tuned display of what the meaning of the data is so they can choose to take action. Next thing, read the docs. When I first started getting into this, I didn't like reading the docs, not even a little bit. And I'll say I love math. But even for me, right, my eyes would glaze over when I say row after row of equations come across. But as I mentioned before, the more you read the docs, the more the terminology will come to you. We'll talk about this in a bit, but don't just copy-paste other people's models. You'll find a tutorial and have a model, and you copy-paste it into a notebook, and it runs, and it works. Good. Don't do that. Either find a data set and use a model that you might find in a tutorial to look at your own data set. Put in some test values and play with that. See if it predicts properly. There's another technique we'll walk through in a little bit that can be really useful to kind of learning how the models are working behind the scenes when you're looking at other people's content. All right, so we'll pause there for a sec. Covered a lot. What questions you got? Yes?
Does Scikit-learn let you use categories as labels for your features rather than numbers, which are really categories? 0 and 1 really mean Cavendish and Apple, or
Sure.
the other way around, but I've already forgotten which one.
Yeah. Does Sklearn or does Scikit-learn allow you to actually use, say, a label? Use the word Cavendish instead of a 0. I do not believe that it does. And I have a head nod, or not a head nod, a head shake in the back. I don't believe it does. They have actual libraries or methods built into Scikit-learn that will do the opposite. You hand it a bunch of Cavendish and apples, and it'll immediately convert them into 1s and 0s for you in an automatic fashion. The other kind of nuance here, and why that might not be a good path to go down, is that typically strings will take up a lot more space in memory than a simple 1 or 2 or 3 or 4. Small integers take up less space in memory. So if you're operating on extremely large data sets and you feel like you've entered in some sort of memory constrained zone, having things reduced down to the smallest amount of memory can sometimes be useful, might speed up processes, etc. So depends on the amount of data you're using and the constraints of your system. I've been stuck on systems where we had small systems, we had lots of data, and we were just stuck. Right? So we had to look at different ways to handle things. All right, what other questions? What you got?
You picked 2 points that were well within their categories.
Sure.
The degree of
Give me a second. Ah, shucks. It's not the one I wanted, but we'll get there. So for example, for some of the naive Bayes, they have techniques to score the accuracy. If you already know the labels and you have the given test data, they have techniques to score some of these. They got the score method, etc. If certain samples have different sample weights, they're strongly categorized in a particular way, you might be able to influence that in various ways. But there are some warnings in some of these cases where they will tell you that some of these things do not, I can't remember where I read it, but one of them mentioned particularly that the predict probability aspect of one of these was not good. It was great for classifying, but predicting the probability of that thing being a thing was a weakness. So what you have to kind of do is just go through each of the different models and get a sense of what's going on with that particular model and really dive into it and figure out, is this model the right one for me? But yeah, I mean, just this morning I was reading about something where it mentioned the prediction capability was a little weird, but the classifying probability was really high. And I think the folks who wrote the documentation even said something to the effect of, this is great for classifying, but don't ever rely on the prediction capabilities. I'm like, what? That sounds so bizarre, but that's just the way it was. All right, what other questions? Anything? Okay. All right. And I totally wish we had time to dive into a whole section on scoring, but we did not. Okay. So, next, I'm going to cut you loose. You're going to read a little bit about clustering. This will be our first foray into an unsupervised learning model. We will not have a classification for any of these things. We're going to ask the model to help kind of group and lump things. But we don't have a known answer for any of these. So, got two different links. Each link has a question associated with that link. So, take a couple minutes and see what we get. I'm going to turn off the thing here, and I'll walk around. Check, check. So, we are about to go live. 3, 2, 1. So tell me, there were 4 cases where k-means clustering might struggle to produce some accurate clusters. Can anybody describe to me some of those characteristics?
If you provide the wrong K,
Say that again.
if you provide the wrong K to the algorithm.
So if you give the wrong number of clusters, okay. And too many what?
Too many dimensions.
Too many dimensions. Where is?
Variance of the clusters
Shucks, I lost my link, folks. Documentation. Go to the API. There we go. API's always got a list over here on the left of all the cool things. There's always Control F.
the battery is about.
My battery's about to die, right? All right. How bad is the battery? Look at that, 5%. Sweet. Okay. User guide, there's that bit. Okay. So here's a case, right? We had a bunch of blobs. We got the wrong number of clusters associated with this thing. We've got data that is not nice round clusters. They're actually kind of these arrays of, I don't know what you call them. They're lines of data points, but they're not round. We've got some data points here where the variance, or how far they spread away from kind of the center, varies. And then we've got some data sets that are unevenly sized, and so that might impact certain things. So as you're looking at, should I use k-means clustering here, or should I use a different clustering algorithm? Some of these things will come up. All right. Next, for the k-means API page, what answer did you folks get there while I plug in my laptop? Well, what answer did we get? 10. All right. And we'll talk about what that 10 means. There we go. In just a second. All right. And we'll talk about why that 10 is there. All right, so, naive base. And, okay. We have electricity. It's all good. So keep that 10 in mind, because we'll come back to it. Wait, we're not doing naive base. What are we doing? Are we doing the next one? K-means. There we go. Somebody's got to keep me on track. Okay. There we go. So the goal of these clustering algorithms, right, is to find data points. If they're similar, put them together in the same group. If they're dissimilar, put them into different groups. Part of the reason they're crazy popular is that they're unsupervised. You don't have to have predetermined labels, so that simplifies certain things. It sometimes makes it more difficult to figure out, did this really work? They can accommodate multi-dimensional data sets, so if you have lots of columns, you can use these, sometimes very successfully. And for simple cases, especially if you can put it on a two-dimensional, three-dimensional chart, they can be fairly easy to interpret. You can kind of look at things and say, yeah, that makes sense, or no, that doesn't make sense. Let's see. Whoops. Like this one right here. We can look at the graph up in the upper right-hand side and say, yeah, that maybe doesn't make much sense. So some of these can be fairly easy to interpret if you can visually display them well. We're going to focus on the k-means clustering algorithm. This thing looks for an arithmetic mean, looks for a mathematical average of all the points in a particular cluster to identify what they'll call the cluster center. So I got a bunch of dots, and it says, all right, the distance from each of the dots to this point takes an average and pinpoints a cluster center. Then what it does when it has these cluster centers, it says, all right, which dots on my graph or which dots in my space are closest to that one, and which ones are closest to other centers, and it will then lump things together based on their affinity or their closeness to the cluster centers that it had determined. We'll talk more in detail about what happens behind the scenes with that, but we'll leave it at that for now. All right. K-means is just one way of doing this clustering. They have things like affinity propagation, dbScan, mean shift, etc. I'll leave it up to you guys to read about some of those. Many of them work similarly, but some of them have nuances where this applies better in this case than another. All right. I'm going to go ahead and import train test split right off the bat because we're going to do that, we know. In this case, I'm going to show you how you can make your own data. I mentioned, sometimes you want to kind of play with this and test things out. Well, if you could make your own data and you could make it within certain confines or constraints, then you have a known good data set, if you will. Scikit-learn has data sets that are downloaded with Scikit-learn when you get it. It also has data sets where they have a small script here that you can use to download much larger data sets. And then they also have the capability to make samples. And so we're going to use make blobs in the samples generator module to make some blobs of dots. All right. Cool thing about their data set generator is it pre-formats your features into matrices and into target arrays. What I'm going to get out of here is a matrix of x and y vectors, x and y dots, that can be plotted on a chart. And then I will get an array of cluster labels. So let's fire this off.
How many features?
In this case, I'm going to have a total of 4 centers, 4 clusters. We're going to have a standard deviation of 0.7. And we're going to look later at what happens if we change that. And I chose for this case to use a random state of 13. And so let's see what we get. And so this thing has 400 samples, and it has 2 features. Basically what's going to be an x and a y variable on a coordinate chart. This is the first 5 records that were randomly generated. 6 and a 9, a 2 and a 5. If we were to plot this on a set of coordinates, these would all be a bunch of dots. If I look at the y, if I look at just the first 5, I have 3 categories, but I had 4 clusters. So I was a little confused, like, hey, did I actually get 4 clusters? I only have 3 categories. So I expanded that a little bit. I only have 3 categories. That's pretty crazy. Let's go take a look at some more. Sure enough. And so I actually do have 4 different categories to go with the 4 cluster centers that I asked. If you've ever run into a snag like this where maybe your data feels like it is not uniformly distributed in some way and you want to see what all your unique values are, NumPy has a NumPy unique function to drop those in, and it'll say, oh yeah, look, Chalmer, here's all your unique values, 0 through 3. And I can confirm that I did actually get 4 different categories. We're going to do a train test split. Notice I opted not to use my own categorization for how big a split to make. I'm going to use the default. Do you remember what the default is for a train test split? 0.25 test size default is 0.25. So 1/4 of my data will be segregated off for testing purposes. The other 75% will be used for training. Let's do that. And sure enough, it made 4 really awesome blobs. Couple things to notice. The blobs are a little egg-shaped or oval-shaped. They're not actually fully round. If you were to look at these, odds are there's probably a little bit of a Gaussian kind of curve here. Certain dots appear more frequently in the center and fewer dots appear on the edge. All right. So let's choose the model. I created 4 blobs. I'm going to tell my k-means model to look for 4 clusters. We'll see what we get. Notice these are all of the hyperparameters that I could set. We're not going to go into what all these mean. We'll talk about n and it later. That's that 10 that you folks looked up. All right. When we do talk in more detail about what happens behind the scenes, more of these will start to make more sense. All right. Let's do our fit. Let's train it on the data that we already have. Okay. And let's do a prediction. Let's look at the shape of the prediction. It predicted 100 categories for us. Hopefully, the categories will work out well. Again, looking at just 5, maybe doesn't show all the categories. Okay. It did come up with 4 categories. That's good. Let's do the scatter plot. So out of the 100 data points that I handed it to test, it was able to segregate these 100 data points into 4 different categories, and I colored each of the categories based on whether it was a 0, 1, 2, 3, or 4. All right, so that part works. All right. So I mentioned that it does this calculation of the big data set, and it tries to find a center. Theoretically, we should be able to get those centers back. We should be able to look at them, and sure enough, you can. Notice that this attribute ends in an underscore. You're going to see several attributes in Scikit-learn that end in underscores, and there's a purpose for that. Anytime you see an attribute that has an underscore at the end of it, it means that was generated by the model. It was a product or an output of the model. If you have an attribute that does not have an underscore, it means that was an input to the model. So let's go see one of the outputs. Let's see what the center cluster or the cluster centers were. These were 4 points that represent the middles of each of those clusters. All right. So I'm going to grab those 4 values and we're going to feed them into a new map. This will be all of our data that we just looked at a second ago, but now I'm going to overlay on that another scatter plot with just those 4 centers. And I'm going to color them white. I'll make the edges black, and I'm going to make them a little bit bigger. And so for each one of my clusters, these black circles are all the places where the centers are located. Okay. So that in a nutshell is a basic clustering algorithm. Many of them work in a very similar way. But how do they work under the hood? Let's talk about that. The k-means model works on a process called expectation maximization. In that process, the model starts off by randomly picking a cluster center. It literally pulls out of the air, you know what, I think the center of this cluster is over here. Boom. Just randomly. It will then go through and it'll say, okay, let me look at all of the points that seem to be closest to this randomly chosen center. It goes, doo, 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 doo. Okay, these points all seem close. These points seem close to this other thing that I randomly picked. And once it figures out who's closest to that, it will then stop, look at just those points, and it'll say, where's the center for each of these? Now that I've picked them, where's the center for them? And it'll choose a new center, and it'll have 4 new centers. It will then do that same process over again. It'll say, all right, now that I've picked 4 new cluster centers, which points happen to be closest to the new cluster centers? Okay, now that I've figured out those, let me see if I can zoom in or tighten up my estimation of where the true cluster center is. And it'll keep doing this 10 times. Right? sorry, roll that back. Rewind the tape. It will keep doing this until it stops getting changes in its answers. It will converge onto an answer, and then it'll stop. Then what it does is it starts all over again. It will start with 4 completely different randomly picked cluster centers, and it'll try and converge a second time, converge a third time, fourth time, and it'll do that process 10 times. That's what the init 10 is. So this thing actually churns through its learning process 10 whole sequences of times. How long it takes to converge may depend on the data and how well it picks a random number. So not only could it have a long convergence cycle, but once it finishes that first convergence cycle, it's going to start all over again from scratch, and it kind of takes a nice average of that. But you can fine-tune that if you wanted to. All right, so let's go back and look at some of these parameters. If instead of doing that process 10 times, you wanted to do it fewer or more times, you can change that. The maximum number of iterations, those kind of things can be all fine-tuned. You can set a random state, which will impact what random locations it might check to start. Those kind of things happen. You can try and set this up to be handled in different jobs if you want to have a distributed system handle this, because it can be laborsome and compute intensive, etc. So there's a lot of hyperparameters we can tune there. And I'm going to stop talking because I don't know anything about any of the others. All right. So what are the gotchas? I mentioned this idea that it tries to converge. It's like, hey, I picked a random spot. Here are things that are close to it. Here's the center of those. And it's supposed to converge. And it converges really well for a small given cluster of dots. But there is no guarantee that it actually finds holistically where the right clusters are. When it throws out a random selection of cluster centers, if it's completely out of whack, it may converge in ways that you don't expect, especially if the data overlaps in various ways. Our clusters were really well separated, so you have no global guarantee that it's going to get the right centers. That is part of why it tries to do a multiple run. The odds of it 10 times in a row finding really crappy random starting points is pretty low. Okay. Another weakness of k-means is you have to decide on the number of clusters. In this case, I made the data, and I'm like, yeah, I want 4 clusters. So I knew to expect 4. But if your data overlaps in various ways, you may not have a good sense of how many clusters there are. There might actually be, if you were to drill into your data, 5 clusters, and you tell it to look for 4. And so it may essentially split one of those clusters up in ways that you might not want. There are different models that can give you a measure of fitness to the number of clusters. Hey, you know what? You're looking at the wrong number of clusters here. Gaussian mixture is one of those. There are some models that have mechanisms built into them to try and determine a suitable number of clusters automatically. As far as speed, clustering algorithms can sometimes be really slow on large data sets, especially if they have to redo the process multiple times. All right, so those are some kind of gotchas that you want to consider. And here's the thing, and this confused me early on. What do those category labels really mean? If I say that, if we were to look under the hood and look at the labels, we might see that this is cluster 0, cluster 1, and cluster 2, cluster 3. Just pretending, right? What do those labels really mean? Well, they don't mean anything. They're just numbers. They don't carry magic. It just means that anything that is labeled with a 0 is related to all the things labeled with a 0. During a subsequent run of the algorithm, what used to be labeled 0 might now be labeled a 1. You'll probably have mostly the same dots in it. And since they're all labeled 1, you know that they're all related to each other. But don't plant any sort of magical association with, oh, everything in this cluster is labeled 0. So next week when I rerun the same model, maybe with a slightly altered data set, I should look for zeros to narrow in on this cluster. Because when you get random starts and convergence, next week's run of this model might say these are all labeled category 1 now. They are randomly determined, so you cannot rely on them always having the same category. All right. To kind of demo this principle, I'm actually going to plot the test data, and I'll plot the training data on the same chart. And we're going to see they're going to have different colors, because in calculating the test data and running the training data, they got categorized in different ways. One of them came up as a 0, one of them came up as a 1, but they were pointing at opposite points on the graph. So to help highlight this, in scatter plots, all our C values are based on whatever labels we provide, 0, 1, 2, 3. The C map is going to map a color to each value. This is the seismic color mapping. It starts at dark blackish, bluish, reddish, and then dark maroon. So I'm going to get 4 different colors out, and that's not what we wanted. Okay. So let's plot both of these on the same graph. These are all clearly clustered together, the training and the test set, but they ended up having different numbers assigned to them. This is probably, maybe 1s and 0s kind of ended up here, 3s and 4s ended up there or something, right? So don't let the categorization, oh, this is a category 0, throw you off. That's all. All right. Lastly, so a little bit on how to learn some more. And we're coming quickly to the end of this show. When you get an error message, take the time to read the error message, even though they are typically scarier than the documentation is. Pay attention to those. While I was putting the lesson together, I actually cobbled together some stuff from different cells in a different Jupyter notebook, and I forgot to copy and paste the .fit. And when I tried to run the notebook, I got this error. It says, hey, you tried to do a prediction, but you never actually fitted it. And it says, this k-means instance was not fitted yet. And it even gave me a little bit of a helpful hint. He's like, call the fit method, right? Which is quite nice of it. But having taught hundreds and hundreds of students over the years, the habit that I see with students is that they often do not read the error message at all. And there's a variety of reasons why they don't. Sometimes the error messages are not written by humans, it seems like. They're written in some gobbledygook that you just can't understand. Some of the error messages may be well written. They might be clear, they might be concise, but you as a beginner are not ready for the data it provided to you. If you were more advanced, it would make sense, but you're a noob, right? So it doesn't, even though it was well written. And sometimes students might do 3, 4, 5 changes to a snippet of code. Like, I'll change this, and I'll change this, and I'll change this, and I'll change this thing, and they run it, and the error message might be about change 1, but they think it's about change 4 because that was the most recent thing they changed, so obviously that's what broke it. And so they'll dive right back at whatever the last thing it was that they changed, because obviously that must have been what I screwed up. And so they miss, in that case, a pointer that points them at, oh, wait. Your inclination is to change whatever you messed with on line 50, but this error occurred on line 3, right? So get used to reading those error messages. It will give you that verbiage, terminology, the grammar, if you will, that you need to know. It will often point you at where the error might lie. It'll help fine-tune you in on, oh, this is on line 20, not line 50, kind of things. I get a lot of error messages, even after programming for years and years, that I look at them and I go, I have no idea what this person is trying to say. No clue. This makes 0 sense to me. So I will copy, paste the error message, put it in my friend Google's lap, and Google will then come back and say, hey, this is what this means. Right? For those of you who want to explore a few more things, we talked about this a couple times. If you are really curious about scoring and validating your models, I've got 2 links here for you. One on kind of the learning curve and what that means, and another one on cross-validation. All right. So looking at the clock, we're at about 17 minutes out. I'm going to let you play with a snippet of code here. I've got a bit of code at the bottom. We'll scroll down and see it in a minute. We're going to make some blobs. These blobs are all set with a standard deviation of 0.7. Right? It's the same 0.7 that we had a few minutes ago. But what I want you to do is I want you to change each of these. You're going to change it to a 1, and then you're going to rerun the code and change it to a 2, and then rerun the code and change it to 3. So you just change this variable right here. A 0.7 is going to give you really tight clusters. As you start to get closer and closer to 3, your clusters are going to spread out. They're going to start to overlap each other, and craziness will ensue. All right. The code is set up to already do the train test split, and it'll produce a scatter plot of just the training data. You will then run the machine learning, and then it's got another scatter plot to show the outcomes of the tests. And I just want you to take a quick glance, if you will, at using make blobs and how that impacts what the model does. Does this have an impact on the model's ability to do its thing? Does it not? Those kind of things. So I'll give you 2 or 3 minutes, play with that. And then, dear Lord, special topics and conclusion. Crap. Nice.
Do you want water or something?
Wait, 440 or 420? Oh, amen. All right. For some reason, I was thinking 420. Okay, we're good.
I wonder why. That's so random.
Yeah. So random. Okay. Go ahead, play with the code a little bit, poke and prod at it. See what you get. Gracias.
Do you want a coffee water, or you don't drink coffee?
There is a water thing right there. If you could give me a bit of water, that'd be amazingly good. Okay, I'm going to turn the mic off. Talk freely. All right. Okay. So we got to get started. Good. So I'm going to run this real quick with a .7, very nicely separated. The standard deviation is fairly tight, so the clusters are small. It's very easy to train this. Everything's good. Let's jump right to 3. I asked you to do all of them, but in the interest of time, we'll just do 3. This one's crazy overlapped. There's things, when I made the groups, when I purposely made the groups, I said create a grouping here and it's going to have category 1, and it did. But that group is fairly spread out. I said make another group to category 2, and that group happened to be spread out, and there's plenty of overlap. So that makes it more difficult for us to figure out, well, should this dot right here, should this one be in what we'll call the red category or the blue category? I don't know. And so as you look at your input data and you look at your output data, you as the data scientist, right, have to try and get a sense for, do I feel comfortable with these results? Maybe do I need to do more testing? Do I need to look at more data? Do I need to find some sort of characteristic of my data that might help me fine-tune which things fall into which categories? If I was to add another column to my data set, might it help me to discern between things that should be in the blue category versus the red category? Those kind of things. And so you might have to change your data. You might have to do some sort of transformation to your data to allow you to look at things in different ways. So there's options, but you're going to run into cases where, I'm not sure what this means. And that'll take time, effort, and research. Questions essentially that came up during the conversation here, how reliable are some of these things? The Scikit-learn folks have a process for accepting new algorithms into the library. Those libraries have to go through kind of an evaluation process. Have those libraries shown up in the literature? If so, do they have citations associated with them where people are using them, referencing them, etc.? Do they have a history, etc.? You can't just be, random Joe, I made an algorithm, it's cool, you guys should include it, and they just suck it in. They look for algorithms that have some runtime behind them and some level of study and rigor. So they're fairly reliable, but you also have to use good judgment. All right, so that's that. Let's go look at special topics. We're going to look at a thing called the polynomials feature method. We're going to look at a technique to create workflows called pipelines. And then we're going to drop polynomial features into a pipeline to look at a topic called underfitting and overfitting. So we'll start off with polynomial features. You can import the polynomial feature class. It has a method associated with it called fit transform. We've seen fit, we've seen predict. I mentioned the word transform before. This one is fit and transform. Okay? It takes input values and it gives you a new series of output values. And a lot of times, people will take these output values that they get from here and they will immediately drop them into other models. Right. What polynomial features does is it will give you a new feature matrix that has all of the polynomial combinations of your original features with a degree less than or equal to the specified degree, which sounds really mathy, and it is, so sorry. As an example, say I had 2 features, feature A, feature B, and I wanted to get the degree 2 polynomial features out of this. When I run my fit transform, I would get back feature A, I'd get back feature B, but I also get back A times A, which is A squared. I get back B times B, which is B squared. I get A times B. And unless I turn it off, I get a column called 1, or I get a value called 1. We'll talk about that in a sec. Okay. You say, well, what the heck? What this is going to allow me to do is to allow me to do some evaluations of data and create curves that may fit my data more succinctly, and we'll talk more about this. I'll show you examples of how polynomial features works, and then we'll see some graphs later in the conversation. Right. So polynomial features is in the pre-processing module. So from pre-processing, we import polynomial features. I'm going to create a very simple matrix. It's only got 3 things in it. It's got a 0, a 1, and a 2. I'm going to drop that matrix into polynomial features and ask it to give me something back. I'm going to start off by asking for degree 1. And it'll give me back a degree 1 polynomial feature set. Right? Unless I turn it off, it's always going to give me a column of 1s, and it will give me back just the A's that I put into it. Pretty straightforward. If I want to get rid of that column of A's, there is an argument that I can include called include bias equals false. We can make that go away. There you go. And so polynomial features with a degree 1 and bias turned off gives me back just the numbers I put in. Easy peasy. Okay. But if I go to degree 2, in this case, I only had 0, 1, and 2. If I square 0, I get 0. If I square 1, I get 1. I square 2, I get a 4. And so I get back a 1 column, I get back my original inputs, and I get back a squared. If I move on to, say, polynomial features 4, I'm going to get back the 1s, my original, a squared, a cubed, and a quad. Right? There's a method to the madness. Bear with me. All right. Let's make a new matrix. It's got 2 columns now, 0, 1, 2, 3, 4, 5. And let's just do a simple 1 degree polynomial features. We basically get back the 1s column, and we get back all of my A column and my B column. If I do a degree 2, we'll get back A column, B column, A squared, A times B, and B squared. And if I do this, it starts to get crazy, and it's all hard to keep track of, so I wrote it out there for you. All right. Again, why does this matter? When I made a simple straight line, just a nice slope, I can say, hey, if I have a slope and I multiply by my x input and I have a y-intercept, this b, I can tell you what y value is. Well, to create different types of curves, you can create different types of equations. And equations can have different degrees. You can use x squared, x cubed, quad. And each of these might have different coefficients, a coefficient of A or coefficient of B. That essentially equates to slopes, if you will. Right? And so if I can feed in different slopes into this formula, I can craft different types of curves. And if my data is not a straight line, I can fit a curve to curved data. The tricky part is what should be A, what should be C, what should be D? What should be those coefficients? What should be the intersects, etc. But to get my data in a format where I have x squared, x cubed, etc., you maybe don't want to do that manually, so you use a tool like polynomial features to take a couple of inputs and craft a broader set of inputs. And once you've done that, you can theoretically make some magic happen, and we'll see it. Okay. That probably didn't make much sense to most folks because there's no visuals. There's a visual at the bottom of this conversation, so just hang on to your hats with that. We're going to move into pipelines, and we're going to come back to polynomial features in a bit. All right. So what is a pipeline? A pipeline is a way to take a scikit-learn estimator, classifier, model, and essentially connect it to another classifier, transformer, estimator, so that you put inputs in one side, the outputs come out, and they go immediately into the next model, and you can chain these together. If you wanted to do that manually, you can. You can say, hey, here's an input. Cool, I got an output. Let me now drop that variable into the inputs of my next model. But that becomes potentially cumbersome. You have to kind of manually handle some of those things. And we can simplify stuff by creating a pipeline. You say, well, what would you need to do with a pipeline? Well, when you're looking at your data, sometimes you need to scale it. And Scikit-learn has a scaler to change things from maybe a wide set of values to a smaller set of values, scale things from random values down to values between 1 and 0, or between -1 and +1, those kind of things. So you might need to scale it. You might need to change it into a new format. We talked about changing stuff into a new format using polynomial features. If you're looking at maybe text, you might want to use a count vectorizer to change things into counts and vectors. You might want to normalize them using this TF-IDF transformer, which is commonly used in text analytics. I think we're not going to say anything else about that. Right? Let's see. All right. So let's make a quick, trivial pipeline example. And I'm going to use polynomial features, and I'm going to use a linear regression. There we go. All right. We're going to use the skin cancer data again because we've seen it and we kind of know what reality looks like there. We change everything into the right formats, feature matrix, we split the data, blah, 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 blah. All right. So everything we just blew through, we've already done. This is the new stuff. I import my linear regression model, my polynomial features model, which we haven't used yet, and I import a pipeline model. All right. Because I just want to kind of show that the pipeline actually works. You feed stuff in, you get stuff out. I'm not going to use polynomial features to make more features. I'm going to use degree 1, and if you remember, degree 1 takes whatever you feed in and gives you exactly that back out. I'm going to include bias equals false so I don't get a column of 1s. So in this case, because it's trivial, I just feed in my data and I get the exact same data right back out. We'll see a case where we use different degrees, but for now, data in will equal the exact same data out. Linear regression, what did I not do? All right. Error message showed up. You should always read the error message. It said, hey, Chalmer, you didn't define linear regression. That's always my cue that I have screwed up as an instructor and I have forgotten to execute a cell. So let's execute it. There we go. Okay. To make the pipeline, you call the pipeline method, and you're going to feed it a list. And the list is going to be full of tuples. Every tuple will have 2 parts. The first part of the tuple will be a name that you type in. I chose to call my first step of my pipeline polyf. And then you tell it what model you want to use for that step. For the next step, I give it a name. I'm going to call it linear R, and I tell it which model to use for that step. Okay? So I created a polynomial features model, and I created a linear regression model. I'm going to feed both of those in the pipeline. And the neat thing here is the pipeline will go into polynomial features, and it'll call fit transform for me. It'll go into linear regression, and it'll call fit for me. I call fit one time, and it'll do all of those steps on my behalf. And it doesn't matter if I have 2 steps or if I have 20 steps. It'll call polynomial features.fit transform. It'll call the next vectorizer fit, and these types of things. It'll do them one by one, and as it gets data out of one model, it feeds it directly into the next model. All right, so let's do this. Fit. It spits out, right? And I told you should always read these things, and sure enough, it reminds me, hey, Chalmer, here's the steps you asked me to take, polyf and linear R. It says, hey, Chalmer, here's the characteristics that you fed into polynomial features. You asked me to be degree 1. You told me to include bias equals false, et cetera, et cetera. Okay. And since I fit the model, I can do a predict, and we'll do a scatter plot. And sure enough, it did match that skin cancer graph the way we expected. Okay. Fairly trivial. I didn't change anything. Didn't really use the power of polynomial features yet, but it works. You make a list. The list has tuples. The tuple has a name and it has the thing you want it to do. You put them in order and magic happens. All right, so let's do the magic on essentially a real-world problem that you might want to look at as you're doing machine learning. Okay, so there is a concern when you do machine learning that you may so tightly constrain the characteristics of your model and you may force it to follow the data so closely that it basically is worthless. It only follows the training data. When I throw new random test data at it, it doesn't work very well. That's called overfitting. And what that looks like in the real world is this. Right? This mattress is clearly overfit for the human that's going to sleep on it. If the human deviates in any way from how this mattress is laid out, this is going to be amazingly uncomfortable. Okay? So you don't want that. Underfitting is essentially the opposite. You maybe draw a line through a set of data. Maybe the data curves down in a big U like this, but you run a line right through the middle of it when you really want to have a line that kind of curves and follows the data. All right, so underfitting and overfitting. All right. There is a link in the documentation here. You can go to a very nice article in Scikit-learn about underfitting and overfitting. What we're going to do is we're going to make a pipeline. We will use the polynomial features methodology to do a degree 1 analysis, which is going to be a straight line, a degree 4 analysis, which will be a curve, and then a degree 15 analysis, which is going to be some really bizarre curve. Okay? So let's start by importing these three things. This function, don't worry about the math. This is basically just going to make a bunch of dots, and they're going to be kind of in a U-shaped curve. All right. So I create the function. I take 30 random values, and there we go. So I have a bunch of random dots in kind of a cosine shape. It's a nice little U. All right. I'm going to produce 100 test values between 0.5 and 1. They're going to be, or 0.05 and 1. They're going to be nicely evenly spaced. And those will be my test values. I'm going to see whether or not I can fit those test values to the input data appropriately once my model is built. All right. So I'm going to take my input data. Degree 1 means I'm going to leave it exactly the way it was, no change. Include bias, false means don't have the ones column. We will then feed the raw input data, which hasn't changed, into linear regression, and we'll get a linear regression out of this. And so I've made a pipeline, and all I have to do is call fit on the pipeline, and it'll call fit on all the other parts for me behind the scenes. There we go. Okay, so we fit. We now predict using my 100 variables or 100 values, and let's plot it. So the blue dots are the raw data that came in. The orange line is what we should see. That follows a very nice cosine curve. And my linear regression gave me this crappy blue line that doesn't quite really work. Right? Doesn't quite follow things. It misses this belly, it misses this spike at the end. No bueno. The magic of polynomial features is that it allows me to make more nuanced curves. And by telling it that, hey, take the original input data and now expand the number of columns in a particular way using the polynomial features method, we're going to have a lot more columns, which is going to allow us to hopefully get a little bit better looking curve. So run that through, predict, and there we go. Nice. Deviates a little bit from the orange up here, deviates from the orange a little bit here, but it's pretty daggum close. Nice. This is probably a pretty good fit. So in this case, by choosing to have done a polynomial features kind of transformation on my data, I managed to find a curve that fits better. The linear regression model was able to determine what coefficients should go into those polynomial features to make a beautiful looking curve. But what if I was a little bit overeager and I'm like, well, hey, shucks, Degree 4 was great. Degree 15 must be amazingly awesome. Right, so we'll go there, degree 15, and now this crazy curve is trying to fit really close to as many of the dots as it can, and obviously this is like crazy, right? So that's overfitting in a nutshell. Okay. All right. We're definitely getting close to the end of the show now. I'll give you a last couple little bits and we'll do the conclusion. Those examples I just showed you of the degree 1, degree 4, degree 15, they came from this example in the documentation. They produced this little article. They have essentially the same graphs. I blatantly plagiarized it, right? This is all of the code that generated that, right? But what they did was they ended up producing a matplotlib figure so they could put all three pictures on the same canvas, if you will. They added certain things in here that maybe weren't necessarily critical to the message. They put the number of degrees into a loop, and they ran this through some sort of a for loop here. And so they kind of produced things in this nice systematic way, et cetera. They added a lot of cruft to do the machine learning and the graphing, et cetera. So what I ended up doing when I was looking at that example and trying to figure out how I could hopefully present it here in this venue, I took that entire process and I looked at it line by line. I'm like, what is that line doing? And do I need that line? What is this line doing? Do I need this line? And I basically pulled out individual lines and I kind of crafted this on my own. And as I proceeded, I ran every couple of lines, like, okay, now it's still working, I haven't broken anything too badly yet. And I stripped away as many of those kind of extraneous complications as I could to really get down to what's the data formatting piece, what's the machine learning piece, what's the visualization piece. And then I crafted that. And I do that regularly when I played with Bokeh and some other types of libraries, right? You see these great examples, the code is really cool, it works, but there's often kind of these complications that they put in there. So if you take a line at a time and you type them in one by one and make sure they're working, that can help you to fine tune on what's going on here. Versus, I mean, I easily could have copied and pasted all of it and said, yeah, let's just run it. But then you're kind of figuring out what's going on in all the other parts that are not critical to the task. So I love to tear apart examples, and I highly recommend it to students. All right, we got 4 minutes. This is the conclusion, section 7. Just a reminder, right? This is the trademarked process. You prep your data, you choose your model, you choose the hyperparameters, you fit the model, you apply the model, and then you examine your results. If you do all of these things, the models will start to make sense. If you miss any of these steps, things start to go a little wonky. Where should you go next? Machine learning is one part of a very sophisticated data analysis system. There's a lot of steps to this. I broke out like 6 of them. The first part is frame the problem. What question am I trying to answer? The next part is data acquisition. How do I get the data? In some cases, you may not have the data, or you might have to set up some system to collect the data. Oh, I want to better understand my customers. Well, are you collecting the right data about your customers? Oh, no, I'm not. Okay. Well, now I need to find a way to collect that. Once you actually acquire the data, then you go into the data wrangling piece, cleansing your data, filtering stuff out, deduplicating records, normalizing records, all that. Typically, somewhere in there, often kind of intermingled, you have some data exploration, look at what the data says, what's going on behind the scenes. Eventually, once you kind of understand your data, you can do some in-depth analysis, and that's where machine learning typically comes into play. Once you've done your machine learning, you communicate your results out. If you are part of a team, you may be lucky enough to get somebody who is adept at some of these steps. like the data acquisition piece or the data wrangling piece. Those are typically ugly, difficult, and hard to manage. They're often also tedious and time consuming. So if you're on a team and you've got somebody who can do that, that's great. For the rest of us, you're going to have to do some or all of that yourself. You say, well, what does that mean? So Forbes magazine had an article on how data scientists spend their time. So this big C over here on this side, this thing is green. It says 60% of your time is spent cleaning and organizing your data. That does not sound like machine learning to me. This section right here, this kind of dark green, that's 19% of your time. That's basically getting your data, acquiring your data sets. 9% is kind of that data exploration, maybe mining data for stuff, right? Some machine learning might occur in there as well. Building trading sets. 4 is going to be refining your very cool machine learning algorithms. And then 5 is going to be other miscellaneous stuff. But the long story short here is you're going to spend very little time doing machine learning. You're going to spend a heck of a lot of time cleaning and refining your data. So when I covered data handling at the beginning of this, that was kind of a precursor to this particular screen, right? You'll want to understand your tools, NumPy, Pandas, those types of things. Understand them well. Because if you have to spend 60 to 80% of your time playing with those tools before you ever get to machine learning, you're only wasting precious, valuable time not knowing your tools. So looking for that. The data visualization piece, right? That comes after the machine learning, but it helps you with your machine learning. It helps you with refining your algorithms. So that's a critical component that you want to kind of focus on. And so that might leave you with, yeah, but what about machine learning? You know, when you walk out of this room, many of you have the data and the libraries installed on your laptops. My machine learning content is up on GitHub. Go through each of these different notebooks, do them again and again. Read the text, refresh your memory on what was said. Look for a learning environment that you learn best in. Chalmer is a huge fan of books. I love books. Some people are not bookish. They prefer videos. They prefer being in a classroom, etc. But find the environment that you're comfortable in. Go to meetups. A lot of meetups have data scientists there, etc. I highly recommend a pet project. Find some sort of data that you would like to model and machine learn. That'll keep your attention. Just doing what's in a tutorial, that kind of sucks. That's boring. And the answer's already there. But man, if you can find a relationship between data and categorizations in data you care about, that's cool. Coffee I don't care about. I don't know why it ended up in my lesson, but it did. Write code every day, and I really mean that. You're learning a brand new language with new vocabulary and new terminology. If you're not using this language every day, much like a linguist, you are not going to get it very quickly. Okay. And lastly, stuff's going to break. You're going to look at wall of code and you're like, oh, I have no idea what's going on. Take a deep breath. Break that code up into parts. Build the code. Type it in yourself, line by line. Figure out what step of the process you're working on. Is this visualization? Is this data wrangling? Separate in a wall of text must-have code to do the machine learning or the visualization from nice-to-have code. Most importantly, don't give up. Be curious. Study hard. Right? This be curious part, that's crazy important for data scientists. And this is your last task of the day. Tell yourself, I've got this, and repeat. I appreciate you folks coming out. I'll be here the entire weekend. If you run into me and you want to ask questions or talk, I'll be happy to kind of chat with you. I really appreciate you coming here and being here. A nuance for you. The funds that you expend here go to support the mission of PSF. They funnel off a little bit to me, and I'm eternally grateful to you guys for that. But most of the funds that you guys spend go to the PSF to help support the mission of the Python Software Foundation. So being here, you have done a great service to helping keep things like PyCon running and on the rails. So I appreciate you. Thank you. I'm going to put a URL up on the screen. they would much appreciate if you guys would take a moment to answer a Survey Monkey. And with that, we'll call it good. I'll stick around.